Yes. Dear aspirants, welcome to the session. Welcome to Scientist Interview Preparation course for BARC, ISRO, DRO, NIC and other PSUs point of. My dear aspirants, myself Surendra Babu, subject Power Electronics. In this session, I would like to discuss most important models of interview questions with respect to power semiconductor devices. This is one of the most important topic in power electronics. Shall we start? Most repeatedly asking questions in power semiconductor devices, mainly MOSFET, IGBT, SCR, GTO, triarc and other semiconductor devices and thyristor family devices, transistor family devices and diode family devices. That is, once we are preparing the interview questions for power semiconductor devices, once you are preparing interview questions from power semiconductor devices, mainly how to concentrate SCR, that is thyristor. Next, GTO, gate turn off thyristor. Triarc, triode AC switch. This is mainly in thyristor family devices. These other types of devices also there. Later on that I will give. In transistor family devices, mainly you have to concentrate BJT, MOSFET and IGBT. These three devices important. In transistor family devices. In diode family devices, you have to concentrate on different types of diodes. In power electronics, power diode concept is important. Power diode concept is important. In this session, with respect to power semiconductor devices, first I would like to discuss what type of models of questions we can expect in interview point of view from MOSFET and IGBT. In transistor family, MOSFET, IGBT, BJT, other transistor family devices. Shall we start, students? Yes. The chapter 1, that is power semiconductor devices. Maximum 2 or 3 sessions I would like to discuss different models of questions with respect to chapter 1, that is power semiconductor devices. This is one of the chapter in power electronics, students. MOSFET versus IGBT in high power pump questions. That means for power applications, MOSFET we are using for signal applications, low power applications. Same MOSFET we are also using for power applications. As electrical engineer, there is a power MOSFET concept. Then IGBT is also used for the at high power level, low power level and high power level. This is high power pump questions, in the sense high power levels. One of the expected question, if the interviewer will ask the question like this, can you compare the switching characteristics between MOSFET and IGBT? Then you try to compare different parameters with respect to MOSFET and IGBT. You try to compare the different parameters. Then what parameters you have to mainly compare? If the question is asked, they don't ask the question first. This question is with respect to comparison of characteristics. This question is not related to draw the characteristics. That question also we can expect. Later that you will see. This question related to compare the switching characteristics. Once the question is asked on switching characteristics now, Switching in the sense, mainly you have to concentrate on the frequency, speed, time. Frequency, speed both are same. Here speed means it is not rotating speed. Na? These are semiconductor devices, sir. All the power semiconductor devices are static devices. If they ask the compare the speed or compare the frequency, both are same. Yes, speed is nothing but a switching frequency. Which device is used for high frequency, which device is used for low frequency. That comparison is important. But here they ask the question only MOSFET and IGBT comparison. One point you have to remember, students. MOSFET is among all the semiconductor devices, MOSFET is highest frequency device. For high frequency applications, we are using MOSFET. Now see what is the answer for this type of question. Compare the switching characteristics. The question is asked, compare the switching characteristics. Mainly you have to compare switching speed. Here switching speed in the sense frequency comparison. In switching characteristics, most important characteristics is frequency. First we have to compare frequency, students. First we have to compare frequency. Then very high speed. This can operate in the nanoseconds range. Then moderate. This can operate in microseconds range. This is time in nanoseconds range. Frequency is very high frequency. Very high frequency. For very high frequency applications, we have to use this. Then IGBT, it's a moderate frequency application. Turn on, very fast to turn on, slightly slower. That is as compared to MOSFET, IGBT is slower. IGBT is slower. Suddenly, if you are writing, before completing all this, they will ask one cross question. Sir, why MOSFET is fast, IGBT is slightly slower? That type of question will arise. Then, yes, MOSFET is a majority carrier device. IGBT is a minority carrier device. Like that you have to answer. Yes sir, MOSFET is a majority carrier device. IGBT is a minority carrier device. See, once the one question is, before you are completing the answer for one question, the cross questions will come. You are answered the question, MOSFET is the majority carrier device, IGBT is the minority carrier device. Again question will come. What is the majority carrier device? Then your answer is, the conductivity is due to only majority carriers. What is the minority carrier device? The conductivity is due to both majority and minority carriers. Even though it is a minority carrier device, the conductivity is due to both majority and minority carriers. Like that, you are ready to face the cross questions. Once you are telling the answer, in that they will ask some cross questions also. For that also, you are ready to face that questions. Like that preparation is required. That type of preparation is required. Once we are preparing for any topic now, all this will be covered in our that is power electronic interview prep or in our interview prep course. All this, not only this subject, every subject will be covered like that. You try to, once you follow whatever we are providing now, then we can easily answer any interview question for any exam, any PSU students. Okay. First, here I am explaining, compare the switching characteristics. What type of characteristics you have to compare? Turn off, very fast to turn off. No tail current. Again, cross question will come here. What is the tail current? Okay, that you will see in the next coming slides. Then this is slow due to tail current. IGBT is slow due to tail current. Then what are the switching losses? Again, question will come. Why MOSFET only tail current? Why not in Why IGBT only tail current? Why not in MOSFET? Like that the question will arise. Okay. Again same answer. IGBT is the minority carrier device. That's why there is a concept of tail current. MOSFET is majority carrier device. There is no tail current. Next, switching losses. This is important. Switching losses are low at high frequency. That's why MOSFET is having less switching losses. That's why it is used for high frequency application. MOSFET is having no switching losses. At high frequency operation also, the switching losses are less. That's why it is used for high frequency application. What about IGBT? IGBT is having high switching losses at high frequency. That's why, as compared to MOSFET, IGBT is used for low frequency application, higher at high frequency. Then control. This is also important. It is a voltage control device. It is a IGBT is also voltage control device. This is important. MOSFET is a voltage control device. IGBT is also voltage control. Again, cross question will come here. Can you explain what you mean by voltage control device? What is the current control device? You are telling that MOSFET is a voltage control device. IGBT is also voltage control device. Sorry. Is there any current control devices? Can you give examples of current control devices? Yes. SCR is the current control device. BJT is the current control device. Again, cross question will come. SCR is a current control device. Is there any other controlling is possible in SCR? Yes, it is also called charge control device. It is also called phase control device. Like that, cross questions also will come. You're ready to face that one. Okay. Yeah. Then it is a voltage control device. It is also voltage control device. Voltage control means by controlling the voltage at gate or by controlling the voltage at control terminal, we can control the output current. By controlling the voltage at control terminal, we can control the output current. That is called voltage control device. What do you mean by current control device? By controlling the current at control terminal, we can control the output current. Finally, output is output. Output is current control. But input side voltage is controlled, voltage control device. Input side current is controlled, then it is a current control device. Yes, sir. Sir, you told that MOSFET is a majority carry device, IGBT is also minority carry device. But why both are voltage control? Why both are voltage? See, that type of questions. Yes, sir. The reason is this one. IGBT is the combination of MOSFET plus BJT. Important question. IGBT is the combination of MOSFET plus BJT. This is important. That is, in IGBT, at input side, the characteristics are similar to MOSFET. At output side, the characteristics are similar to BJT. That's why IGBT is the combination of MOSFET plus BJT. Clear? Like this, you have to answer this question. Compare switching characteristics means like this parameters we have to compare. Next. Now, can you draw the switching losses versus frequency characteristics for IGBT and MOSFET? Sorry. Here I am explaining only IGBT and MOSFET. Can you plot the switching losses versus frequency characteristics? Yes. This is MOSFET and this is IGBT. From this curve, what is your observation? Yes, sir. If frequencies increases at high frequency, the switching losses are more in IGBT, less in MOSFET. See, for same frequency of operation at high frequency, for same frequency of operation, IGBT is having the high switching losses and MOSFET is having the less switching losses. Okay, this is our observation. That is, for frequencies increases now, then switching losses proportional to frequency. Switching losses are proportional to. This is switching power loss. Switching power loss. This is switching power loss. Then what is the relation between, if the question is asked, switching energy loss and switching power loss? What is the relation between switching energy loss and switching power loss? The switching energy loss equal to the switching power loss into frequency. This also you have to. This is the switching energy loss. Switching energy loss. That is switching energy loss equal to switching power loss into frequency. Clear? Okay, this observation is important. The question is asked, plot switching losses versus frequency characteristics. Clear? Next. This cross question. Why IGBT is preferred in high power applications as compared to MOSFET? Generally, MOSFET is used for low power, high frequency. IGBT is used for high power, low frequency. Low frequency in the sense as compared to MOSFET is a low frequency. That is, point to remember students, in frequency application, in frequency point of view, which is for high frequency, MOSFET is used for high frequency as compared to IGBT. But in power applications point of view, IGBT is high power applications as compared to MOSFET. Related to this, how the question will ask. Why IGBT is preferred in high power? Then this is the reason. IGBT is preferred in high power pump drives due to its high voltage handling capability and lower conduction losses, while MOSFET is limited by high conduction losses at such readings. That's why. The reason is IGBT is used for high power application because of high voltage handling capacity and lower conduction losses. But what about the MOSFET? This is having less voltage handling capacity. Less voltage handling capacity. And this is having high conduction losses. High conduction losses. Not switching losses. High conduction losses. Because of this reason, MOSFET is limited by high power applications. That's why if you compare the switching losses, in switching losses point of view, which is high switching losses? IGBT is high switching losses as compared to MOSFET. But in conduction losses point of view, then MOSFET is high conduction losses. MOSFET is conduction losses is high as compared to IGBT. Okay, this is the reason. This is one of the reason. Because of switching losses are less in MOSFET, that's why it is used for high frequency. IGBT is having less conduction losses, conduction losses are less, that's why it is used for high power. Like this also you have to explain. If they ask the question, have some minimum knowledge on that topic related to that one. If they ask one question, if you answer different answer, then no use. Clear? See, why IGBT preferred in high power? Then suddenly you can answer like this. Yes, sir. This is more voltage handling capacity, less conduction losses. Then why MOSFET is limited in such applications? Because it is having the lower voltage capability and whose conduction losses also like that you have to explain. Next. That's why at low frequency IGBT is acceptable. At high frequency IGBT losses becomes very high because switching losses are more. That's why MOSFET is preferred. Then final conclusion point here. MOSFET is high frequency low power application. IGBT low frequency high power application. That's like pumps and motors. How to prefer the IGBT. Why IGBT is preferred in high power applications? Like this you have to ask. Clear? Next. All these questions with respect to IGBT and MOSFET. Already in previous interview questions, na this IGBT and MOSFET, so many questions they framed. They are asking. That's why first I selected this topic. Next, one more possibility of questions. Can you plot the switching characteristics of MOSFET and IGBT? Can you plot the switching characteristics of MOSFET and IGBT? Yes, you ready to plot the characteristics like this. Okay, this is the MOSFET. This is MOSFET switching characteristics. These are the MOSFET switching characteristics. See, once you try to draw these characteristics, they absorb how you are drawing. You are perfectly drawing, just started perfectly, then they don't want draw the total characteristics. That's why your starting must be perfect, more perfect. Once you draw just one characteristics as he knows this characteristics, then they will ask another question. They don't draw all the characteristics like this, but they will check. Yes, they are having some knowledge of plot. They are drawing the characteristics are related to that one or not. Once they ask the MOSFET and IGBT characters, you are drawing diode characteristics, then they know, yes, is wrongly drawing. You have some knowledge. Yeah, this is MOSFET characteristics. MOSFET switching characteristics. MOSFET switching characteristics. That you have to concentrate. And this is IGBT switching characteristics. IGBT switching characteristics. Characteristics. Yes, friends. Then these are the switching characteristics. That in switching characteristics again there is a turn on time and turn off time. Turn on time is nothing but a TDN plus TR. This is called turn on time. Like this, they will ask the, can you write the formula for turn on time? Can you write the formula for turn off time? Turn off time. What is TDN? This is the turn on delay time. TR is the right time, rise time. This is turn on delay time. Turn on delay time. TR is the rise time. Rise time. This is TDF, turn off delay time. This is the turn off delay time. And this is the TF is the fall time. It's not final time, it's a fall time. Like this you have to explain. If they ask the formula, can you write the what is the turn on? What is the turn on time of the MOSFET? What is the turn off time of the MOSFET? Then what is the total time of operation spreads? T on plus T off. Can you explain a relation between switching frequency and turn on time and turn off time? Then what is the F equals to 1 by T? This is called switching frequency. This F is the which one? Switching frequency. Switching frequency. F is the switching frequency. That is what is the observation here. If on time, off time or decreases now, or the total time of operation decreases, then what is the frequency? Increases. If any device is operated for high frequency, its turn on time and turn off time must be less. Its turn on time and turn off time is less, then that device is used for the high frequency application. That device is used for the high frequency applications. Clear? That you have to concentrate. Come on, students. Yes. Yeah. Like this, we can also expect for the IGBT. If they ask the what is the turn on time for the IGBT, same TDN plus TR. TR is the rise time. TDN is the turn on delay time. Then what is the T off? This is different here. Turn off time. TDF plus TF1. This is TF2. This is fault time 1, fault time 2. But here some extra time it is taken. Fault time 2 is fault time 1, fault time 2. This is the IGBT switching characteristics, turn on time and turn off time. We can also expect the questions like this. Can you define the rise time in this characteristics? Can you define the delay time in this characteristics? That type of questions also we can expect. You ready to answer? Okay. What the rise time? See this one. From this point to this point, this is taken as a rise time. And this is the turn on delay time, this point to this point. Just by seeing the characteristics, you are ready to explain the what is the turn on delay time, what is the rise time, what is the fault time. Yes. Okay, this is about the question related to draw the switching characteristics. Next. Can you show tail current region in switching characteristics of IGBT? Sorry. Students, I told already. IGBT is used for low frequency application because it's a minority carrier device. MOSFET don't have any tail current, but IGBT is having the tail current. In this question, in this characteristics, one more possibility is, can you show the tail current region? Yes. This region now, here only one fault time. This is only one fault time. Here there is a two fault times. This is TF1. This is TF1. This region is TF1. And this is TF2. Turn off time 2. Okay, this region is nothing but a tail current region. This is after falling time 1, there is still the device is conducting. That is nothing but a tail current region. Because of this extra current, because of this extra time, turn off time of devices increases. When the turn off time of devices increases, what I told, T equal to T on plus T off. T on plus T off. When the turn off time of devices increases, what the total time of operation increases. If the total time of operation is increases, friends, then what is the frequency? Frequency decreases. Okay, because of this tail current, then IGBT is having the low frequency application as compared to MOSFET. Like this. Again, the cross question will come. What do you mean by tail current? Why tail current in IGBT? Why not in MOSFET? That's the characteristics. Okay, you drawn the characteristics. Yeah, perfectly you answered. And they asked again, can you show the what tail current region in the IGBT characteristics? Yeah, perfectly you shown that reason also. Again, the cross question will come. Why tail current in IGBT, but why not in MOSFET? Why not in MOSFET? If the question is asked like this, then we can explain like this. IGBT is a minority carrier device. IGBT is a minority carrier device. So many times that I told. During on state, electrons plus holes are injected into the drift region. Drift region. Again, cross question will come. Can you show what is the drift region in MOSFET or in IGBT? Then you have to draw the structure to show the drift region. That questions also will come. These charges get stored inside the device. Whatever the minority charge carriers are there, these are stored inside the device. Then during turn off, what happening? Gate signal is removed quickly. In IGBT, there is a gate signal. That signal is removed quickly. But stored holes remain, they recombine slowly. Because of this slow recombination, causing tail current. So tail current due to stored minority carriers. If the question is asked, why tail current in IGBT? Directly you answer the question, due to stored minority carriers. That is your answer, sir. Don't explain like this. Now, this why I have explained. If they explain, if you explain, then you can explain like this. Only one statement question now. Why tail current in IGBT? Your answer is because of minority carriers. Then what is the answer for this one? Tail current is due to minority carriers, stored minority carriers. First answer this one. Due to stored minority carriers. Then what about my MOSFET? MOSFET is a majority carrier device. Only electrons are holes. Only electrons are only holes. Based on the P MOSFET, N MOSFET. P MOSFET, which are the majority carriers? Holes. N MOSFET, which are the majority carriers? Electrons. Electrons are the majority carriers. P MOSFET, which are the majority carriers? P MOSFET, which are the majority carriers? Holes. N MOSFET, which are the majority carriers? Electrons. That's why here I am telling that only electrons are holes. Depending on the type, P MOSFET or N type, N MOSFET. Conduct no charge storage in drip region. See this one. Here there is a stored charge inside the device, but there is no charge storage in the drip region. Then during turn off, when gate voltage is removed, channel disappears instantaneously. No stored charge, current drops immediately. But here current is not drops immediately. So no tail current in MOSFET. If gate is removed, the current drops immediately, then no tail current in the case of MOSFET. Tail current is present in IGBT because of stored charges in the drip region, or because of stored charges due to stored minority charge carriers. But in MOSFET, there is no any tail current. Once gate is removed, immediately the current drops to zero. That's why there is no tail current in MOSFET. Okay, like this you have to answer students. Sorry. Yes, concentrate. Yes. Concentrate students. One more question. If the question will ask like this, can you draw the basic structure of MOSFET and IC? Yes, you try to draw these figures. This is the structure of MOSFET. This is the structure of IC. Draw these characters. Yes. Yeah, this is the structure of which one students? MOSFET. Structure of IC. Can you show the drip region? Yes, this is the drip region. This is the drip layer. In this case, drip layer is which region? N minus. This is also N minus region. What is the N minus layer? Because of N minus, this N minus layer is also called intrinsic layer. What is the name of this one? Intrinsic layer. Can you give what is the advantage of intrinsic layer? Yes, sir. It supports high blocking voltage. It supports high blocking voltage. It supports high blocking voltage. Intrinsic layer supports the high blocking voltage. Okay, that you have to consider. Okay, you drawn this structure of MOSFET and IGBT. After drawing this structure, then cross questions will come like this. Okay, you drawn these two structures. Can you show the structural differences? What are the structural differences? What are the structural differences here? Yes. Sir, here n plus region, here also n plus region, this also p region, this also p region, and this is n minus region, this is n minus region, this is n plus region, this is also n plus region. But extra, there is a p plus, but here there is no p plus. IGBT is a p plus extra, but here there is no p plus. You have to show like this. Then how to answer that cross question? The structural differences between MOSFET and IGBT. This is also important. What is the structural differences between MOSFET and IGBT? Mainly, you have to answer these structural differences. With respect to structural differences, layers. You have to compare layers. Power MOSFET is a 4 layer, but power IGBT is a 5 layer. Extra P plus layer is not present in the power MOSFET. Yes. In layers point of view, power MOSFET is how many layers? It is a 4 layer. I am talking about power MOSFET. Power IGBT is having the 5 layers. Then extra P plus layer is present in IGBT, but there is no extra plus P plus layer in the case of MOSFET. Clear? Then what is the carrier type? That you already know. It is a majority carrier, but it is a majority plus minority. Majority plus minority generally treated as a minority carrier device. In general, minority carrier device is nothing but a combination of majority carriers plus minority carriers. That's what is a in general minority carrier device. In general, minority carrier devices. Then structure, mass structure, mass plus bipolar structure. Mass structure in the sense metal oxide semiconductor structure. Metal oxide semiconductor. Terminals. What are the terminals of MOSFET? It is having the source, drain, gate. Source terminal, drain terminal, and gate terminals. It is having the source, drain, and gate terminal. What about power IGBT? It is having emitter, collector, gate terminal. The terminals of power IGBT. IGBT is also having 3 terminals. MOSFET is also having 3 terminals. But layers are different. Then conduction. During conduction, it just like acts as one resistor. Important. And power IGBT is replaced as a voltage drop. That is, for example, how this MOSFET is modeled. MOSFET is modeled as a one resistor during conduction. This is the on-state resistance. Then what IGBT is modeled as a? IGBT is modeled as a one voltage drop. One voltage drop. during conduction. During conduction. During conduction, it is modeled as unsteady resistance. Then it is modeled as a voltage drop. If the question is asked, during conduction, it is modeled as unsteady resistance. Then how to calculate conduction losses? Conduction losses. If the question is asked, how to calculate conduction losses? Then with respect to resistance, now you have to calculate. This is I RMS square into R. But in this case, how to calculate conduction losses? Then in this case, the conduction losses equal to, this is average conduction losses equal to, this is the P conduction, is equal to VD into I average. This you have to calculate. If it is in terms of voltage drop, now, if it is in terms of voltage drop, you have to calculate VD into I average. If it is in terms of, yes friends, if it is in terms of then resistance, now to calculate the conduction losses, you have to use I RMS square into R. I RMS square into R. Clear? That you have to consider. Like this, you can explain for structural differences. Internal action, there is no BJT action, but PNP transistor action is present. In the case of our IGBT, that I told now, this IGBT is the combination of, this is MOSFET plus BJT. So internal BJT action is takes place. BJT action is takes place. The fundamental question all of you know, can you abbreviate this MOSFET, metal oxide semiconductor field effect transistor? This also you have to. This is a very fundamental. Don't ask me. It's very fundamental. Metal oxide semiconductor field effect transistor. Field effect transistor. Then what about IGBT? It's insulated gate bipolar transistors. Gate bipolar transistor. Sorry. Gate bipolar transistor. Insulated gate bipolar transistor. Like this abbreviation you have to remember. This question with respect to structural differences. Next. One more important questions with respect to BJT and MOSFET. What is parasitic BJT and parasitic diode in MOSFET? What is the parasitic BJT and parasitic diode in MOSFET? And why parasitic diode is advantage in inverters? One important point you have to remember, friends. MOSFET is generally, internally it is a built-in diode, built-in anti-parallel diode. Built-in anti-parallel diode. That diode is nothing but parasitic diode. The question here it is asking that why parasitic BJT and parasitic diode in MOSFET. A parasitic NPN bipolar junction transistor exists between the source and drain. This exists between the source and drain. This is the parasitic. The question is asked where this parasitic transistor will exist between source and drain. The P-type, this is also important. Which acts as a base? P-type acts as a base. N plus region acts as a, this N plus region acts as an emitter. And N minus layer acts as a collector. N minus layer acts as a collector for parasitic transistor. Yes, sir. Here, source is connected to both base and emitter of parasitic base. The source is connected to both base and emitter. The source is connected to both base and emitter. This is the base and this is the emitter. For this emitter and base also, which is connected, source is connected. This is connected. Source is connected. It is connected. It's just like a short circuit. Once it is a short circuit, na, and therefore BZ is always in the cutoff state. Then what is the current through the collector? The current through the collector equal to 0. Then it is always in which region? Cutoff state. Important. A parasitic transistor in MOSFET. A parasitic transistor in MOSFET is a always cutoff state. This transistor is always in cutoff state. Why? Why it is in cutoff state? Because the reason is this also. This collector and base and emitter is connected to source. It is short circuit. Yes. Where the parasitic transistor is formed, for parasitic transistor, which is the emitter, which is the base, which is the collector. A parasitic transistor always operate in cutoff state. Why? This type of questions also you can explain. Next, where the parasitic diode is formed. The parasitic diode with source acting as anode and drain is cathode. This one. Source is acting as a anode. Drain is acting as a cathode. Important. Which is the source? Anode is the source. Then which is the cathode? Drain is the cathode. May be used in half bridge or full bridge rectifiers. But here important one strikes. The parasitic diode is also shows that the reverse voltage blocking capability of the power MOSFET. This inbuilt diode is an advantage in inverters. This is important. That's why this is known. Why it is advantage in inverters? This parasitic diode it is an inbuilt anti-parallel diode. Anti-parallel diode in MOSFET. It blocks reverse voltage. This feature is required in inverters. This is the advantage. This feature is required in inverters. In inverters, this feature is required. This you have to remember. This parasitic diode, this parasitic diode is the anti-parallel diode. This feature is required in the inverters. That you have to remember. Yes. Is it okay? What is parasitic BZ8? What is the parasitic BZ8 in MOSFET? Or the parasitic diode in MOSFET? In parasitic BZ8, which acts as an emitter, which acts as a collector, which acts as a base. For parasitic diode, for parasitic transistor, always operate in cutoff state. Why? That base and emitter is connected to source. This is connected to source. This is also connected to source. It's just like a short circuit. What is the collector current? 0. That it is operating in cutoff state. In parasitic diode, this which is source is anode, which is cathode, drain is cathode. Which region is cathode? N plus region. Which region is anode? P region. Like this we can expect options. This feature is required in inverters. There is one feature is required for the inverters. Inverters are required bipolarity unidirectional devices. Bipolarity device. Bipolarity in the sense both the side blocking capability is required. So because of this reverse voltage blocking, because of this reverse blocking capability. This reverse blocking capability is required in the case of inverters. Mainly in which inverters? Inverters in the sense voltage source inverter, this is required. This feature is required in voltage source inverters, not in current source inverters. Okay, next friends. Again, one more important question in IGBT. Why latch up in IGBT? Explain parasitic thyristor in IGBT. Parasitic transistor and parasitic diode in the case of MOSFET. But why latch up or parasitic thyristor in IGBT? Important students. In IGBT, there is a formation of anti-parallel connection of two transistors. The IGBT, there is a two transistors. It's a back-to-back, not anti-parallel. It's you have taken back-to-back connection of two transistors. This back-to-back connection of two transistors. Which transistors? PNP transistor and NPN transistor. This is NPN transistor. This is PNP transistor. Because of back-to-back connection of two twin transistors, there is one thyristor is formed. You know, a thyristor is the equivalent to back-to-back connection of two transistors. It is a back-to-back connection of back-to-back connection of two transistors. What are those transistors? That is PNP. First one is NPN transistor. Another one is PNP transistor. NPN transistor. Another one is PNP transistor. Clear? Then this back-to-back connection of two transistors, it is equivalent to thyristor. Like this you have to explain. Equivalent to thyristor. This thyristor is nothing but a parasitic thyristor. IGBT structure has two inherent transistors Q1 and Q2, which constitutes a parasitic thyristor. This is the equivalent to thyristor. What do you mean by latch-up? This is important. Latch-up occurs when this internal thyristor gets unintentionally turned on. When thyristor is on, gate losses its control. When the gate losses its control, that is the operation of the thyristor. You imagine, you already know what is the operation of the thyristor. Once the thyristor starts the conduction, gate losses its control over the anode current. Like this. Here also there is a formation of parasitic thyristor. In IGBT, because of the formation of parasitic thyristor, once gate losses, once it is on, IGBT is on, gate losses its control over the current. Then there is a uncontrolled current. This uncontrolled current may damage us the IGBT. That is the problem. Simple, sir. The question is asked like this. Why latch up in IGBT? Yes, sir. In IGBT, there is a back-to-back connection of two transistors, NPN and PNP transistor. This indicates thyristor. Because of thyristor structure in IGBT, once it starts conducting, gate losses its control. Once gate losses its control, and the current is uncontrolled current. Because of uncontrolled current, IGBT will damage. That's why latch-up is advantage or disadvantage in IGBT. It is a disadvantage. But latch-up is advantage in SCR. SCR latch-up is advantage. That's why SCR is a latching device. Okay. We are designing for latching in the case of SCR. But IGBT is not designed for latching. How SCR is designed? As a latching device. Latching device means even though gate is removed, that SCR continuously conducts. Like that, that is required in the case of SCR. That is advantage. But IGBT, we are not designed for the latch-up. Latch-up in the sense, even though gate is removed, continuously conduct. That property is not required in IGBT. Like that we are not designed. Even though we are not designed, because of this structure, there is a SER formation. Because of that SER formation, parasitic thyristor formation, there is a latch-up. Because of that latch-up in IGBT, current will continuously increase. There is uncontrolled current. Because of that uncontrolled current, IGBT will damage, sir. Like that you answer, sir. Cross question will come here. Is it latch-up is advantage or disadvantage in IGBT? Yes, it is a disadvantage. But where the latch-up is required in a thyristor, sir, because where power applications we want latch-up, even the gate is removed, continuously it will conduct. But in IGBT, no need to gate is removed. Gate is continuously applied in IGBT. That is the control device. That is a semi-control device. SCR is a semi-control device. IGBT is a fully controlled device. Controlling is required here. Gate losses is not required. Like that you have to answer. Clear, sir? This is one more important question in IGBT. Next. Why does latch-up happen? Latch-up happens due to high collector currents, high temperature, excessive voltage, improper device design, or triggering of parasitic transistor. Because of this, a latch-up is. What do you mean by latch-up? Even though gate is removed, even though control terminal is removed, it will continuously contact. Even though control terminal is removed, it will continuously contact. That is a latch-up. Why latch-up is happening? This is the reason. Is latch-up is an advantage? No, it is a disadvantage in IGBT. It is a disadvantage in IGBT, sir. Because no control from gate after latch-up can cause thermal runaway. Temperature also continuously. What do you mean by thermal runaway? A cumulative increase of temperature. Again, question will cross question. A cumulative increase of temperature. A cumulative increase of temperature. A cumulative increase of temperature. Cumulative increase of. Then leads to device failure also. It leads to device failure also. This is the latch-up is not advantage in the case of IC. Then how to handle, how to prevent in the case of IC? Then we have to limit the collector current, reduce the dV by dt, proper gate drive circuits are required, use fast production circuits, temperature control, modern IGBT design. One more important here, cross question. Can you explain how to reduce dV by dt? Then your answer is snapper circuit. Using snapper circuit. Using snapper circuit. Snapper circuit. Again, questions related to snapper circuit later on the time. Here cross question is using snapper circuit, dV by dt is reduced. Clear, students? That you have to concentrate. Again, cross question will come like this. Latch-up is an advantage in SCR. It allows the device to remain after triggering without continuous gates, making it suitable for power control application. That I told now. Latch-up is advantage in SCR, but it is not advantage in IGBT. That's why SCR needs latch-up, works on its own. IGBT must not latch up, needs control. It is a semi-controlled device, it is a fully controlled device. For controlling purpose, not be latch up. That's why gate must control everything in IGBT. If latch up happens, gate useless. That's why I told now IGBT is a fully controlled device. Gate is control everything. If it is a latch up is happening, gate loses its control. Then useless. Gate is useless here. That's why. So latch up is a disadvantage in the case of IGBT. Latch up is a disadvantage in IGBT. Clear, friends? That you have to concentrate. Next, one more possibility of question. Next. Can you draw the transfer characteristics of MOSFET and IGBT? Yes. This is the MOSFET transfer characteristics. This is the IGBT transfer characteristics. Then what are the cross questions will come? What is transfer characteristics? Then relationship between output current and gate voltage. Which is the output current in the case of MOSFET? Drain current. Which is the output current in the case of IGBT? Collector current. Why IGBT curve steeper than MOSFET? IGBT curve is steeper than MOSFET due to minority carriers injection. What happens below threshold voltage? This is after threshold voltage it starts conducting. After threshold voltage it starts conducting. Below threshold voltage, if you take the below threshold voltage, what happening? The device is in off state. Below threshold voltage, the device is in cut off state. Device remains in off state. What does slope of curve indicates? What does slope of curve indicates? If you find the slope of this curve, current by voltage, that is the transconduction. This indicates the transconduction. Which device has high transconductance? Transconductance. That is, IGBT is having the high transconductance. Why MOSFET is faster despite lower current? No charge storage. Why MOSFET? This is already given. Why MOSFET is faster? No charge, no storage. It is a majority carrier device. Like this, cross questions also we can expect. Next, one more question. In this, one more cross question. Here you draw the MOSFET transfer characteristics, IGBT transfer characteristics. Can you draw the transfer characteristics of MOSFET? P channel MOSFET, N channel MOSFET, enhancement MOSFET, depletion MOSFET, like that. The questions will explain. If that type of questions are asked, then based on the type of MOSFET, how to draw the characteristics. This is the N channel, the arrow mark must be in. How to remember? N channel in. Simply remember, for N channel, the arrow mark must be in. Into the channel. This is the N channel depletion type MOSFET. This is the symbol. This is the characteristics. This is the P channel depletion type MOSFET. P channel arrow is outside, out direction. Then it is the depletion MOSFET. What is the difference? You see this one. Depletion type and enhancement type. This enhancement channel is depleted, divided here. But enhancement in depletion type channel is not divided. Simply remember, depletion type channel is not divided, but enhancement type channel is divided. Depletion not divided, but enhancement channel is divided. N channel, the arrow mark must be in. N for in, like that you remember. P channel, the arrow mark is out. P channel, arrow mark is out. Like this we have to remember. These are the symbols and related characteristics. This also you have to remember. The question is asked, draw the characteristics of the N channel depletion type, P channel depletion type, N channel enhancement type, P channel enhancement. This is the P channel, and that is enhancement type, P channel enhancement type. Okay, like this we have to draw the characteristics for MOSFET in different cases. Okay, so generally you can get the characteristics of this one. Slightly this side. You can get the characteristics like this also. Okay, next. And one more important question is, can you write the symbols? Can you draw the symbols of IGBT and all types of MOSFET? IGBT. Then, if the question is asked, this is a simple question. IGBT symbol. Minimum fundamental. This is the minimum fundamental. The question is asked, what is the IGBT symbol? This is the IGBT symbol. Then what are the terminals of IGBT? This collector, emitter, gate. This is collector, this is emitter, and this is the gate. This IGBT symbols. Can you draw the MOSFET symbols? In MOSFET, so many MOSFETs. No? First, I am drawing N channel, N channel. This is enhancement, enhancement. N channel, enhancement MOSFET. In enhancement, channel is depleted. This is gate. Enhancement. In depletion, channel is not depleted. This is the drain, gate, source. Then it is N channel. N channel in the sense into. Arrow mark is in. Next. P channel, enhancement MOSFET. This is already given symbols. Once again, here. This one. This is enhancement type. Channel is depleted. Enhancement MOSFET. Then it is a P channel enhancement MOSFET. Same, but arrow mark is different. N channel in, P channel outside. Then you have to take arrow like this. This is drain, source, gate. Then if it is asked N channel depletion type. N channel depletion. N channel depletion type. Can you draw this one? Depletion type now. In depletion, channel is not depleted. This one. This is N channel. Arrow is in. Drain, gate, source. If it is asked P channel enhancement, so depletion. P channel depletion. P channel depletion type. Then you have to draw like this. In P channel depletion type now, layer is not, that is channel is not depleted. This is the gate. This is drain, source. Same, but arrow is P channel out. P channel is like this. You have to answer. Okay, this how to draw the. This is N channel depletion enhancement MOSFET. This is the P channel. This is P channel enhancement MOSFET. P channel enhancement MOSFET. This is N channel depletion type MOSFET. This is the P channel depletion type MOSFET. Like this, one question mechanism. Next. One more important is, can you draw the ideal characteristics of IGBT and MOSFET? Yes. If they ask the question like this. Ideal characteristics of IGBT and MOSFET. First you draw the symbol, IGBT symbol for IGBT. Can you draw the ideal characteristics of IGBT? Yes. For IGBT, if it is asked, this is the gate, This is collector. This is emitter. Point to remember, all these semiconductor devices, power semiconductor devices, if it is asked for ideal characteristics, now without any diode, with these characteristics are without diode. Let this is the current, this is voltage. Without any diode, these devices are operated in the first quadrant. It blocks the forward voltage, it allows the forward current. This IGBT. That's why it is a which devices? Unipolarity, unidirectional devices. Unipolarity in the sense only one polarity of voltage it blocks. Unipolarity and unidirectional device. Unidirectional device. Then can you draw for MOSFET now? In general, MOSFET is asked, you have to take the without any diode. Without inbuilt diode I am taking. Then for MOSFET symbol already you know. Once again, if you want, I am trying here. For MOSFET, you take it may be N channel or P channel, whatever may be. This is a gate, this drain, source, collector. Then this is also, if you draw the ideal characteristics of this MOSFET, both are having same ideal characteristics, but practical characteristics are different, but ideal characteristics are same. This V minus V. It is also first quadrant operation. Unless otherwise, if there is no diode, you have to take the first quadrant. Then it is also unipolarity, unidirectional device. Unipolarity in the sense, this is important. Unipolar is different, unipolarity is different. Unipolar device in the sense majority carrier device. Unipolar device. These are the majority carrier device. Unipolar in the sense majority carrier. Unipolarity in the sense only one polarity is blocking. Bipolarity in the sense both the polarity, positive voltage, negative voltage, that is blocking. Don't confuse here. Unipolar is different, unipolarity and unidirectional device. Both the ideal characteristics are same here. Unidirectional device. This also MOSFET is also unipolarity, unidirectional device. IGBT is also unipolarity. But IGBT is the bipolar device. Don't confuse. Polarity is different, polar is different. Bipolar device. Bipolar device in the sense, this is the minority carrier device. The conductivity is due to both majority and minority carriers. Minority carrier device. Minority carrier device means the conductivity is due to both majority and minority carriers. Majority carrier device in the sense, the conductivity is due to only majority carriers. Sir, but here also majority carriers are there. Yes, that's why I am telling them inherently, if there is a minority carriers and majority carriers, generally it is treated as a minority carrier device. If only majority carriers, then only it is a majority carrier. Majority carrier device is also called unipolar device. Minority carrier device is also called bipolar device. But polarity is different. Sir, but you are telling us polarity, bipolar, unipolar. That I am telling. Polar is different polarities. Polarity in the sense with respect to voltage. This is with respect to voltage blocking. Voltage blocking. How many voltages it is blocking? Only one voltage. This is also polarity. How many voltage it is blocking? Only which voltage? Positive voltage. Sometimes we can also expect the questions like this. For example, if they given like this. This is IGBT. IGBT. Insulated gate bipolar transistor. This is collector. This is emitter. And this is the gate. If there is any anti-parallel diagrams, this IGBT with anti-parallel diagram. we can expect the questions like this also. IGBT with anti-parallel and MOSFET with anti-parallel. But I told already in MOSFET inherently there is a parasitic diode. This is the anti-parallel. Anti-parallel. But because of this anti-parallel diode, this is IGBT with anti-parallel diode. This is MOSFET with anti-parallel. Because of this anti-parallel diode, it also allows the current in the reverse direction. Sorry. Here I told one statement where it is required. Mainly this point you have to correct it. Inbuilt diode. This is bipolarity. Future is required. Then it is blocks reverse voltage. Not here. This feature is not required. In MOSFET, in built-in anti-parallel diode is there. Because of built-in anti-parallel diode, it allows reverse direction. Then bidirectional capability. This is bidirectional capability. This feature is required in inverters. In which inverters? Voltage source. Important. Anti-parallel diode allows the reverse direction also. Only diode is there, it blocks. But MOSFET with anti-parallel diode allows the current in the reverse direction. This bidirectional capability, bidirectional current capability. Then both the direction conduction. This feature is required in voltage source inverter. You please correct it. Voltage source inverter. Okay. Now, then because of this anti-parallel diode, without diode it is operate in which quadrant? Without this diodes, if there is no anti-parallel diode, this is I, this is V. Which quadrant? First quadrant. Because of anti-parallel diodes, because of this anti-parallel diodes, it allows the current in the reverse direction. Now the characteristics are changing. Now it becomes which device? Unipolarity bidirectional. Unipolarity and bidirectional devices. Like this. If the question is asked like this, across the IGBT or MOSFET, if there is any anti-parallel diode is connected, how these characteristics will change? Extra we can get negative current. If there is no diode, only positive current. Because of anti-parallel diode, negative current. One more question, students. If the question asked like this, in series with IGBT, if one diode is connected, or in series with MOSFET, if any one series diode is connected, this is gate. If any one series diode is connected like this, not anti-parallel, series diode, then how these characteristics will change? Now this character will change like this. If there is anti-parallel diode, because of parallel connection, there is a reverse current. This is I, yes friends, this is minus I, this is V, this is minus V. Without diode, it is a first quadrant. Because of series diode, now it blocks reverse voltage. This is important. Sorry. Because of series diode, negative voltage. Now how these characteristics are changing? Now it becomes a unidirectional bipolarity device. Unidirectional. But here bidirectional device because of anti-parallel. Okay, because of series diode, unidirectional and bipolarity. Bipolarity in the sense both the polarity, positive voltage and negative voltage. Bipolarity device. Okay, like this we can expect the questions on ideal characteristics of devices. Next, and one more possibilities. They will ask the questions with respect to application point of yours. This is the final question. MOSFET and IGBT application. Can you give what are the applications of MOSFET? Mainly general applications of chargers, SMPS. That is practical applications. switch mode power supplies, computers, DC to DC converters, in electronics. In these applications, mainly we are using the MOSFETs. For these applications, we are using the MOSFETs. Why? Why? Why these are preferable? Because of fast devices, no tail current, high switching frequency. Because of this reason, we are preferring these devices in this application. Because these applications are required fast switching. But where IGBT is used, heavy load applications means high current, high power applications, train, metros, industrial motors, high power inverters, welding, heating applications, we can use the IGBT. See the differences. Where in practical application point of view, where you can use MOSFET, where you can use IGBT. Why? Why these applications we are using IGBT? Handles high voltage and current, strong power capability. It handles high voltage and current. Strong power capability is there. That's the reason why we can use IGBT for this application. This is high voltage and current capability. Current capability. And high power capability. We can use this. Then, but nowadays the trend is replacing IGBT with silicon carbide MOSFETs, SiC MOSFETs. In EVs also, electric vehicles also, we are replacing the IGBT with MOSFET, but MOSFET is SiC MOSFETs we are using. Then high frequency is possible, high power application is also possible. The reason is this one. Faster, more efficient, less loss. Nowadays, the trend is going this one. Yes, friends, this is about the session. In this session, in interview preparation point of view, I given the how the questions we can expect in power semiconductor devices. But in this session, in power semiconductor devices chapter, I explain about related to MOSFET and IGBT. In the next coming sessions also, first I have to complete other models of questions in power semiconductor devices. After that, we go for the chapter wise in rectifiers point of view, inverters point of view, AC voltage controllers, cyclo converters, how the in drives point of view, how the questions will we can expect. What models of questions we can expect in interview point of view, that I would like to discuss. This is about the session. Thank you. Dear aspirants, welcome to the session. Welcome to Scientist Interview Preparation course for BARC, ISRO, DRO, DRDO, NIC and other PSUs. Students, myself Surendra Babu, subject Power Electronics. In the continuation of interview prep course with respect to Power Electronics, I am discussing the most important models of questions in power semiconductor devices. In the previous session, I completed some questions. Then continuation of that, we'll see other models of questions with respect to power semiconductor devices. Students, all of you, welcome to the session. Shall we start? Yes. This is a chapter 1 related questions, that is the power semiconductor devices. One more important model of question, that is the most expected model of question, that is the thyristor commutation failure questions, that you have to concentrate on. Thyristor commutation failure case questions. The question will ask like this, friends. What causes of commutation failure? Students, all of you well know this. If the question is asked like this, if the SCR is not properly turned off, then the SCR will be commutation failure. It is subjected to commutation failure. If the SCR is not properly turned off, what do you mean by proper turn off of the thyristor? We have to apply the reverse voltage up to the anode current through the SCR reduced below a minimum value of current. That current is called holding current. Then only SCR is properly turned off. If the SCR is not properly turned off, then there is a commutation failure. What causes of commutation failure? That is, if the SCR is not properly turned off. If the SCR is not properly turned off, then commutation failure is exist. If you answer like this, then one cross question will come here. What do you mean by proper turn off of thyristor? For proper turn off of thyristor, we have to apply the reverse voltage in such a way that the anode current through the SCR must be reduced below a minimum value of current. That is, for proper turn off of SCR, reverse voltage across the SCR, must be applied up to anode current through the SCR, anode current through SCR reduced below a minimum value of current. What is that minimum value of current? Is called holding current. We must apply reverse voltage up to anode current to the SCR is reduced below a minimum value of current is called holding current. Again, a question will arise like this. Can you write the relation between circuit turn off time and device turn off time? Yes. Important. Always for proper turn off of thyristor, for proper commutation of the thyristor. What do you mean by commutation? The process of turn off of SCR is called commutation. The question is asked like this. The process of turn off of SCR is called commutation. If they ask the question, what do you mean by commutation? The process of turn off of SCR is called commutation. Then for proper turn off of thyristor, what is the relation between circuit turn off time and device turn off time? Important steps. For proper turn off of SCR, always important relation. the circuit turn off time is greater than device turn off time. What is TCS? Circuit turn off time. Circuit turn off time. What is TQ? The device turn off time. Device turn. If the question is asked, can you write the relation between the circuit turn off time and device turn? Yes. Circuit turn off time equal to safety factor into some safety factor. Safety factor into device turn off. This is the relation between circuit turn off time and device turn off time. Again, question will ask like this. What is the difference between the circuit turn off time and device turn off time? Yes. Device turn off time is the time taken by the device to complete its turn off process. For turn off of SCR, how much time it takes? That is the device turn off time. What is the circuit turn off time? It is the time taken, reverse voltage applied across the device. But up to we can apply reverse voltage up to the anode current is reduced below the holding current. Yeah, this is the device turn off time is the time taken by the device to complete the turn off process. Circuit turn off time is how much time you are applying reverse voltage. But you can apply the reverse voltage more than the device turn off time. For example, students, the SCR is taken to complete its turn off process later 50 microseconds. But you can apply reverse voltage more than 50 microseconds. Sir, why? Within 50 microseconds the SCR is going to turn off. Why you are applying more than 50 microseconds? That I am telling now. Proper turn off of SCR. Still, if there is any minority carriers are present, you have to remove that minority carriers. Then to eliminate the commutation failure. To overcome the problem of commutation failure, always we can apply the reverse voltage more than the device turn off time. Understand? That's why I am telling that circuit turn off time always greater than the device turn off time. Circuit turn off time is greater than the device turn off time. What causes commutation failure? If the SCR is not properly turned off, then there is a commutation failure. What do you mean by commutation? The process of turn off. Can you write the relation between circuit turn off time and device turn off time? The circuit turn off time is greater than device. Then circuit turn off time equals safety factor into device turn. Again, one more question will arise here. Holding current. You use the term holding current. What is the holding current and what is the latching current? Can you write the relation between latching current and holding current? This is a minimum fundamental questions now. Can you write the relation between latching current and holding current? Yes. Students, we know that always latching current is greater than the holding current. Latching current is associated with turn on process. Holding current is associated with turn off process. These points also mainly you have to concentrate. Latching current related to turn on process. That is for turn on of SCR, which is the reference, latching current is the reference. For turn off of SCR, which is the reference, holding current is the reference. Yes, that relation I will write. Then the commutation failure mainly caused by, what is the reason for commutation failure? AC voltage dip. Because of dip in the voltage, because of reduction of the voltage, supply voltage, there is a commutation failure. High load current, because of high load currents also there is a possibility of the commutation failure. Larger firing angles and source inductance, because of source inductance and larger firing angles also there is a possibility of commutation failure. Yes friends, this you studied in the rectifiers also. Now this source inductance concept is important in rectifiers. We know that in a rectifiers, because of the source inductance, then the outgoing SCR is not properly turned off. When the outgoing SCR is not properly turned off, then automatically incoming SCR will turn on, then both the SCRs will conduct at a time. There is a commutation failure because of the outgoing SCR commutation failure. If both the SCRs are conducting at a time, there is overlapping of the SCRs. Because of overlapping of SCR, the output voltage is going to reduce. Okay. That is commutation failure mainly caused by voltage dip, high load current, large firing angle at source impedance. Then which reduce available turn off time or reverse voltage for the thyristor. Then which reduce the available turn off time or reverse voltage for the thyristor. That means if you apply the reverse voltage for less time, you are not applying sufficient time for reverse voltage, then automatically commutation failure takes place. That I told now. You must apply reverse voltage. Sir, why you have to apply reverse voltage? To turn off the SCR. What do you mean by turn off? We can apply the reverse voltage across the SCR and reduce the current below some minimum value of current. That is, current is nothing, holding current. Then up to what time we can apply? We must apply reverse voltage up to current is reduced below the holding current. If you are not reduce the current below the holding current, then SCR will not turn off. If the SCR is not turned off, that is called commutation failure. Yeah, that points you have to remember. Here I have to write what is the device turn off time. If they ask define the device turn off time, device turn off time. It is denoted by TQ. It is time taken by the device to complete its turn off process. It is, yes friends, time taken by the device. Time taken by the device to complete its turn off process. Complete its turn off process. Turn off process. Then what is the circuit turn off time? Circuit turn off. If the question is asked, can you define the what is the circuit turn off time? It is the time taken. How much time reverse voltage is applied? It is the time taken. Reverse voltage applied across SCR. If the question is asked like this, is it during device turn off time current is reduced below the holding current or during circuit turn off time? Yes. During device turn off time itself current is reduced below the holding current. Even though current is reduced below the holding current during device turn off time itself, but extra time you can apply reverse voltage for proper turn off of thyristor to overcome the commutation failure problem. Extra time. That's why I told that TC must be greater than TQ. Next. Can you write what is the latching current and holding current relation? The latching current is always greater than the holding current. What is this latch? IL stands for latching current. Latching current is always greater than the holding current. What is this IH stands for? Holding current. Holding current. Then we know that it is associated with which process? Turn on process. It is a reference for turn on process. Important points. It is associated with turn on process. Turn on process. Then holding current associated with the turn off process. Associated with turn off process. Turn off. Is associated with the turn off. Then latching current is always greater than holding current. Then latching current equal to 2 to 3 times of holding current. This is important. Latching current equal to 2 to 3 times of holding current. This relation is also important. latching current is, this is 2 to 3 times of holding current. That you have to remember. Clear? This, with respect to what the question it is asked, based on this question, what causes of commutation failure? Commutation failure is nothing but if the SCR is not properly turned off, there is a commutation failure. Then if you want to make the proper turn off, like this you have to prepare. If any cross questions will ask, these questions we can expect students. That you have to concentrate. This is one question. This is most expected model of question. Next. In the same concept, if the question is asked, in the same commutation failure concept, can you draw the plot versus voltage versus time? Can you draw the, can you plot voltage versus time curve? Yes. Here I am drawing the normal commutation, that is successful commutation and commutation failure case. In normal commutation, a sufficient reverse voltage is available. This is the reverse voltage. Students, you know that to commutate the SCR, to turn off the SCR, to commutate the SCR, a reverse voltage is applied across the SCR. A reverse voltage applied across SCR. To turn off the SCR, what you have to do? A reverse voltage is applied across the SCR and current is reduced below minimum value of current, that is nothing but a holding current. Now see, this is during extinction. That is extinction in the sense the current going to reducing. During this extinction, a sufficient reverse voltage is applied. This is which voltage? Reverse voltage. The sufficient reverse voltage is applied across the SCR. Because of that reverse voltage, the current through the SCR is falls to 0. When the current through the SCR is falls to 0, then SCR is perfectly commutated. Then in this case, SCR is perfectly commutated. SCR is perfectly commutated. Perfectly commutated. This is under normal operating condition, normal commutation condition. That is outgoing SCR. Outgoing SCR in the sense the SCR going to turn off. Get sufficient reverse voltage. Current through T1 falls to 0. Then commutation is successful. That's the reason why the SCR is perfectly turned off. Now the question is, during commutation failure, what the curve we can expect? Listen. There is a possibility of commutation failure if this reverse voltage is less value of reverse voltage is applied, or the reverse voltage is applied very less time, or less reverse voltage is applied. When the magnitude of reverse voltage is reduced, when the magnitude of this reverse voltage is reduced, then the current through the SCR is not falls to 0. Still SCR is conducting, students. The T1 SCR, outgoing SCR, still it is conducting. Still SCR is conducting, then it is called commutation failure. Why? This voltage is going to reduce. Reverse voltage is small for very short duration. We applied for very short duration. That is less than the device turn off time we are applied. That I told now. Reverse voltage must be applied up to circuit turn off time. But we applied the reverse voltage is less than the device turn off time. Because of this less reverse voltage, the current through the SCR is not going to turn off. When the current through the SCR is not going to turn off, it is continuously conducting. Listen, students. Let this SCR is the outgoing SCR. Outgoing in the sense that SCR going to turn off. If SCR is outgoing SCR, this is outgoing. One is outgoing, there is some incoming SCR. Let T2 is the incoming SCR in any particular circuit. Let this is the incoming SCR. This SCR is not turn off, but already incoming is not turn off, but already incoming SCR is turn on. Now both the SCRs are conducting. There is a overlapping of the devices. Both the SCRs are conducting. There is a overlapping of the devices. There is a overlapping of the devices. Okay, that is nothing but here commutation failure is happening because of less reverse voltage. Yeah, this explanation I given. There is overlapping. Overlapping in the sense both the devices conduct at a time. Both the devices That is incoming as not only both the devices, that depends on the type of circuit again, but simply remember incoming SCRs and outgoing SCRs conduct at a time. Incoming SCRs and outgoing SCRs. Outgoing SCRs conduct at a time. Conduct at a time. Then current does not fall to zero, SCR continuously conduct because of less reverse voltage. This is the less reverse voltage. Because of this less reverse voltage, that SCR is not going to turn off, then it is continuously conducting. Then incoming SCR, outgoing SCR, both are in on state. There is overlapping of the devices. This situation we can see in the rectifiers. If you take the example is with source inductance. With source inductance, there is overlapping of the devices. You know that in a single phase full wave rectifier, due to source inductance, all 4 SCRs are overlapped. In 3 phase full wave rectifier, 3 SCRs are overlapped. 3 SCRs are overlapped. Then because of overlapping, the output voltage will be reduced. But the problem with overlapping students, the output voltage will be reduced. This I given. Reverse voltage across outgoing SCR is insufficient. This is the insufficient. Current does not fall to zero even after omega T2 also. Outgoing SCR continues to conduct. Commutation failure is occurred. Commutation failure is occurred. Yeah, this, if the question is asked, plot voltage versus time curve. This is the voltage versus time curve. Voltage versus time curve for normal commutation. If commutation is success, then this type of curve we can get. If the commutation is failure, students, then we can get this type of curve. Like this you have to explain. The question is asked, can you plot the voltage versus time curve during commutation condition? We can explain like this. Clear? Next. One more question, students. In the same commutation failure situations, what is the real life scenario? In real life, what is the for this commutation failure? What is the real life scenario? Then there is a voltage dip. Voltage dip takes place in HVDC system, controlled rectifiers in industries, power grid during faults. That I told now. Voltage dip takes place in HVDC system, in converters. Mainly in converters, voltage dip takes place. In controlled rectifiers in industries also voltage dip takes place. Because of reduction of the voltage, there is a commutation failure. Power grids during faults. Power grids during faults also voltage dip takes place. Let's consider this is the actual voltage in a power grid. Then real life event, voltage dip in power grid, heavy load switching or during fault condition, this voltage dip takes place. Because of this voltage dip is present in the converters now, then there is a commutation failure. You have to explain like this. This is the real life scenario for the voltage dip. Then in which cases voltage dip takes place? HVDC system. In a high voltage DC transmission system also, we are using the converter at the input side and output side. At input side we are using rectifiers. At output side we are using inverters. Then there is a voltage dip, there is a commutation failure. So, shall we continue? Yes. This is one more question that you have to concentrate. Next. In the same commutation failure cases, in the normal condition, then there is no voltage dip. Normal condition, there is no voltage dip. During voltage dip, that is during fault condition, there is a voltage dip. That is voltage is going to reduce it during fault condition. Sufficient reverse bias available for TQ, then thyristor will properly turn off. Then normal voltage condition, thyristor is properly turned off. In voltage dip condition, take the example fault condition. In fault condition, reverse voltage does not reach the required level, insufficient time for TQ, then thyristor does not turn off. That is called commutation failure. Commutation. This is a real life scenario. Then because of this one, let actually T1 still on state. If it is during reverse bias, T1 must be turned off. But T1 still on state, T2 is also still on state. Then there is a commutation failure. Both T2 and T1 conduct simultaneously, causes short circuit across AC source. It causes the short circuit across AC source. Sorry. Yes, friends. This effect on thyristor conduction. Yeah, this is the real life scenario. We can explain like this. If the question is asked to explain in real life scenario, then because of the voltage dip, then the reverse voltage is reduced. Once the reverse voltage is reduced, then commutation failure takes place. That is, supply voltage suddenly drops, commutation voltage reduced, thyristor does not get reverse bias. When the thyristor does not get reverse bias, then result is commutation failure. This is one more important question that you have to concentrate with respect to commutation failure cases. All these questions with respect to commutation failure cases. Okay, here I explained the commutation failure cases now. Sorry. In the first case, what the causes of commutation failure that I explained. Then plot voltage versus time curve that I explained. That is, I explained the normal cases and commutation failure cases also. Give the real life scenario example that I explained. This totally 3 examples, 3 questions that I explained. Okay, next. One more type of question, same for the commutation failure cases. What happens during voltage dip? Then what is the system response during voltage dip? Like that also we can expect the questions. What happens during voltage dip? If any voltage dip takes place, what happens? Yes, AC supply voltage suddenly drops. That all of you know this. Whenever the voltage dip takes place, AC supply suddenly drops. Yes. AC supply suddenly drops and commutation voltage available thyristor is reduced. What happens if the voltage is? That's the same case that I explained. Commutation voltage is reduced. Sorry. Yes. Yes. That is, during voltage dip, AC supply suddenly voltage dip takes place. Voltage drop takes place in the AC supply. Whenever voltage drop is exists in the supply, sufficient voltage is not available for the commutation of the thyristors. Thyristor does not get sufficient reverse bias voltage. Commutation failure is occurs. High current flows, heating stress will increase. So this is the problems during voltage dip. The question is asked like this. What happens during voltage dip? We can explain like this. Then what is system response? What is the system response during voltage dip? Control system detects disturbance. Then automatically what disturbance is there, that is detected by the control system. Then automatically firing angle may be increased to restore the margin. To improve that voltage, control firing angle may be increased. If failure persists, converter is blocked or tripped. Then automatically the converter operation will be blocked or tripped. Crowbar protection may be activated. Mainly in the case of HVDC, voltage dip takes place in HVDC converters also. Then automatically crowbar protection is activated. Why, sir? To protect the total circuit, to protect the converter, to protect the converters, then crowbar protection is used. We know that. What is the crowbar protection? A crowbar protection used for the protection of the converters, not a single SCR. It is used to protect the converters. Why the name is given as a crowbar protection? We are using crowbar thyristor. What do you mean by crowbar thyristor? A high rating thyristor is called crowbar thyristor. Then what do you mean by crowbar protection? This crowbar protection is used to protect converter. To protect the converter. In crowbar protection, yes students, in crowbar protection, a high rating, a high rating thyristor is used. A high rating thyristor is used. A high current rating thyristor. A high current rating thyristor is used. A high current rating thyristor. High current rating SCR. Thyristor is used. High current rating SCR is called crowbar SCR. High current rating SCR. Current rating SCR is called crowbar. A high current rating SCR is called crowbar SCR or crowbar thyristor. What do you mean by crowbar thyristor? Highest current rating SCR is called crowbar SCR. This also will be questions. What do you mean by crowbar thyristor? High current rating SCR. System waits for voltage recovery and restarts. This is the final system response that you have to. All these questions, whatever I explained now, these questions related to commutation failure. What do you mean by commutation failure? Then how to overcome the commutation failure? Draw the response characteristics. That is a plot time versus voltage versus time response characteristics. Okay. This and what happens during voltage dip? What is the system response? What is the practical scenario? This mainly how to explain like this. These are the most important models of questions that asking in the interview. That is for your interview. Yeah, that is for PSUs. Any PSUs, you have to consider BARC or ISRO or any PSUs. These models of questions. Next, one more type of question that is framing thyristor commutation failure in grid fault. If there is a fault, same concept. It's a grid fault related. That I told already. Na? If any fault takes place in a grid fault, then voltage dip takes place. Because of the voltage dip again, the voltage is not sufficient to reverse the SCR. Sufficient voltage is not available for the reverse bias in the SCR. If that voltage is not sufficient to reverse bias the SCR, then automatically commutation failure takes place. One point to remember, students, for this type of questions. To turn off the SCR, we have to make the reverse bias. We must apply the reverse voltage up to the current through the SCR reduced below the holding current. Must reduce below the holding. Otherwise, commutation failure. SCR will not turn off. What do you mean by commutation failure? SCR will not turn off if sufficient reverse voltage is not available. Here the question is, during grid fault condition, yes, grid fault, voltage dip. Once voltage dip takes place, sufficient reverse voltage is not available for reverse bias the SCR. Once sufficient reverse voltage is not available to reverse bias the SCR, then commutation failure. This one. This is the normal condition voltage. During grid fault condition, the voltage is reduced. Voltage dip. This is the voltage dip duration. If the voltage dip duration is present, this reverse voltage is reduced. The reverse voltage applied across the SCR is reduced. During grid fault, supply voltage reduced suddenly. Commutation voltage available to SCR is reduced. Then commutation failure. This also commutation failure related during grid fault. This is commutation failure. Under normal condition, this voltage is sufficient for reverse bias of the SCR. This voltage is, if you apply this much of voltage, there is no commutation failure. But during fault condition, the voltage is reduced. When the voltage is reduced, there is no sufficient voltage for reverse bias of the SCR. then SCR will be turn off. Plot voltage versus time curve during grid fault condition. The question is asked like this, then explain like this, friends. Clear? That you have to concentrate. Next. Plot current overlap period. Yeah, that I told. Because of the commutation failure, there is overlapping of the devices. There is overlapping of the devices. Which are the overlapping of the devices? That is, T1 is conducting, T2 is also conducting. Current through outgoing SCR, still it is conducting. Then suddenly who comes into the action? Incoming SCR going to turn off. Incoming SCR, T2 is also conducting. Then this is the overlapping. Overlapping in the sense, both the devices are conducting. During overlapping. Why there is a overlapping? Because of commutation failure of the T1. If T1 is turn off now, there is no overlapping. If the T1 is turn off now, there is no overlapping. But because of commutation failure, this commutation failure of SCR, T1. Commutation failure. Failure of T1. Then here T2 is on, here T1 is conducting. Then during overlapping, both the SCRs will conduct. Both the SCRs will conduct. Both the SCRs will conduct. That is, during voltage dip, overlap angle increases. Both SCRs conduct simultaneously. Commutation failure is possible. This is happening because of the. This is the question related to again commutation failure. Plot current overlap period. Current overlap period. This is the current overlap period. This is current overlap period that you have to consider. That is, T1 is conducting, T2 is also conducting. Next. Why SCR fails to turn off? That I told now. If you don't apply sufficient reverse voltage, simply you can answer like this. Why SCR fails to turn off? If sufficient reverse voltage, not applied in sufficient time, then SCR fails to turn off. This is the reason. If sufficient reverse voltage is not applied in sufficient time, or if anode current, in terms of current also you can, if anode current is not reduced, below holding current. If anode current is not reduced below holding current, then also below holding current, then SCR will be fails to turn off. SCR turn off when reverse biased for a minimum time. It is reverse biased only for a minimum time. It is not reverse biased for sufficient time. Minimum time only it is reverse biased. In grid fault, voltage dip reduces the reverse voltage applied across the SCR. During grid faults also, the voltage across the SCR is reduced. Then there is a fail of the turn off of the SCR. Reverse voltage may not reach the required level or duration. Sufficient reverse voltage we are not applying. Insufficient reverse bias and time, SCR does not regain forward blocking gap. It will not turn off. Turn off is nothing but we have to bring the SCR from during turn off. What do you have to do, students? During turn off, we have to bring the SCR from forward conduction mode to forward blocking mode. We have to bring the SCR from forward conduction mode to forward blocking mode. But we are not bringing to forward blocking mode because of insufficient reverse bias and insufficient time it is applied. Outgoing SCR continues to conduct along with incoming SCR. That is because of the overlapping also commutation failure. This causes commutation failure. Both SCRs will on. The both the SCRs on, there is a commutation failure. Okay, these are the why SCR fails to turn on because of the commutation failure. Like this we have to explain. Clear? All these questions related to commutation failure. See how many number of questions they ask. Yeah, this is the most important models of questions. Next. Okay, there is a commutation failure. If the question is asked, what are protection methods? What are the protection methods for this commutation failure? The question is asked like this. What are the protection methods for the commutation failure? Yes, you have to make the firing angle control. Increase firing angle during voltage dip. That I told. What alternative measures you have to take for protection? That is the firing angle control you have to take. Crowbar protection, that is HVD system. Crowbar protection will activate. Voltage monitoring is important. Continuous monitoring of AC voltage. If dip detected, if there is a dip in the voltage, it takes corrective action. Fast fault detection and blocking. Automatically you have to make the blocking of the converter. System recovery. After voltage recovers, reset system and restart converter in controlled manner. These protection methods you have to take care. These are the protection methods you have to employ for the commutation failure. The question same related to commutation failure related question. If the question is asked, what are the protection methods? There is firing angle control, crowbar protection scheme. That is mainly in HVDC system, high voltage DC transmission system. Voltage monitoring. Sir, in HVDC also we are using converters. In that converters there is a SCRs. Correct or not? In HVDC, at sending end there is a rectifier to convert AC to DC. At receiving end there is inverters to convert DC to AC. In HVDC system, we are using the converter station. We are using converter stations in HVDC system. Okay, this is the rectifiers and these are the inverters. This is at sending end station, and this is at receiving end station. Receiving end station. This is HVDC. In HVDC system. This is in HVDC system. That you have to consider. Next. Okay, these are the different protection schemes employed for the SCR. If the question is asked, what are the different protection schemes? Different protection schemes employed for the SCR. Employed for SCR. This is also important that you have to concentrate on. What are the different protection schemes employed for SCR? This is called SCR protection circuit. SCR. If the question is asked, can you draw the SCR protection circuit? Draw the circuit like this. If the question is asked, can you draw the SCR protection circuit? This is SCR protection circuit. In this SCR protection, after drawing the circuit, the question will ask like this. What is the purpose of using this circuit breaker? CB in the sense circuit breaker. Sorry. Circuit breaker. Circuit breaker. Then what is FACLF use? FACLF students. FACLF in the sense fast acting current limiting fuse. Fast acting current limiting fuse. Fast acting current limiting fuse. FACLF. Then what is the purpose of using these protection devices? For overcurrent protection. Then what is the purpose of using inductor? for di by dt production. For di by dt production. Inductor for di by dt production. Di by dt production. For di by dt production, inductor is connected in series with SCR. Where it is connected? Inductor is connected in series with SCR. This is it. Then VL equal to L into di by dt. You have to design the L value. L equal to VL by di by dt. You have to use this formula. This inductor is also called L's number. L's number. Generally, snuffer circuit means RC circuit, friends. This is called L's number. What is the purpose of using L's number for di by dt production? You know property of inductor. Inductor cannot allow the sudden change of current. Inductor important cannot allow sudden change of current. Sudden change of current. Okay. Inductor cannot allow sudden. That is the purpose of using the inductor. What is the purpose of using varistor? This varistor or metal oxide varistor or non-linear resistor. Metal or MOV. Metal oxide varistor. Metal oxide varistor. Metal oxide varistor, or it is also called thyrector. Thyrector. If the question is asked, what is the purpose of using this one? Over voltage production. Over voltage production. Over voltage production. For over voltage production, we are using MOV, metal oxide varistor, or thyrector, or non-linear resistor. Next. What is the purpose of using snuffer circuit? Generally, snuffer circuit means RC circuit. This is for dV by dt production. dV by dt production. Okay. This snuffer circuit is used for now. This across the SCR. Across the SCR, we have to connect R and C. This is RS now, and this is the CS now. This is called snuffer circuit. We also connect the diode. Now the question will ask like this. This RC snuffer circuit. RC snuffer circuit used for dV by dt production. This production scheme is important. dV by dt production. But the question will ask like this. How this will protect? Because of the capacitor. Capacitor cannot allow sudden change of voltage. Capacitor cannot allow sudden change of voltage. Sudden change of voltage. Like this, it will protect. That's why it is protect. Then one more question will arise like this. Okay, then capacitor is enough. Why resistor we are using? Yes. The purpose of using resistor is to limit the discharging current of capacitor. Otherwise, SCR will be damaged. To limit that is the purpose of using resistor. What is the purpose of using resistor? To limit the discharging current of capacitor. Discharging current of capacitor. Capacitor. Otherwise, yes friends, otherwise, what happened? SCR will damage. SCR will damage. Otherwise, SCR will damage. To limit discharging current of capacitor, otherwise SCR will damage. Then what is the purpose of using diode? What is the purpose of using diode? This total is the snuffer circuit. To bypass the resistor. To bypass the resistor. To bypass the resistor during charging of capacitor. Charging of capacitor. Important. See, actually this resistor is required during discharging of the capacitor. Whenever capacitor is discharging, that current is limited by resistor. But during charging time, this resistor is not required. That's why to bypass this resistor, a diode is used. To bypass the resistor during charging of capacitor. Now we have the one more question they will ask. Okay, if this resistor is present during charging, what happens? Then additional power loss, then time constant also will increase. If resistor is present during charging, if resistor is present during charging, if resistor is present during charging, then power loss increases. Then what is the time constant? Charging time constant is also increases. That is, for charging of the capacitor, it takes more time. Time constant increases. These are the problems. If resistor is present during charging. That's why to bypass this resistor during charging of the capacitor, a diode is used. Yeah, this type of questions we can expect from the snuffer circuit. But simply remember, students, generally snuffer circuit means it is RC circuit. You take RC circuit. That is dV by dt production. If the specially they given like this, L snuffer, then di by dt production. Why the name is given as a snuffer? It suppresses reduces the dV by dt. It cannot eliminate. Important. Snuffer circuit, RC circuit over voltage product. What is RC circuit? dV by dt production. To reduce dV by dt. Not for elimination of dV by dt. To reduce dV by dt. This is di by dt production to reduce di by dt. Not for elimination. Important. If the question is asked like this, can you tell it's a eliminate or reduce? Yes, it is a reduces. That is important. And one more important values they will ask. What is the range of di by dt? If they ask the range of di by dt, generally 20 to 500 ampere per microsecond. Ampere per microsecond. How to take 20 to take this is the 300 amperes per microsecond. 20 to 500 ampere per microsecond. If they ask what the range of dV by dt values, range of dV by dt values 20 to 500 volts per microsecond. Volts per microsecond. This also you have to tell. If they ask the range of dA by dt and dV. Then if they ask the how to design this snuffer circuit resistance, how to design snuffer circuit capacitance, snuffer circuit resistance. I told already one formula is V equal to L into di by dt. From this you design the L value. V by di by dt. Then in order to design the CS value, IC equal to CS into dV by dt. Or we can also use the CS formula like this. CS equal to 2 zeta by RS plus RL whole square into L. This is the design formula, students. Design formula. What is zeta here? Damping coefficient. Damping coefficient. Damping coefficient. Or damping factor. Take this is the damping factor. Damping factor. For zeta, what is the zeta in the case of snuffer circuit? You have to take the 0.5 to 1. If you take the point, if it is not given, you take approximately it is a 0.65. For better design of the snuffer circuit parameters, I'll take this one. If it is asked what the RS value, how to design the RS value, you take V equal to I into RS. From this, you have to make the dV by dt equal to di by dt into RS. From this, you design the RS values. Okay, like this, you have to write. And one more possibility is, what is the purpose of using heat sinks? Heat sinks for temperature protection. To protect the device from high temperature rise. Protection from high temperature rise. Protection of SCR from high temperature rise. Protection of SCR from high temperature rise. High temperature rise. To protect the SCR from high temperature rise, we are using the heat sinks. HS in the sense heat sinks. Heat sinks. We are using heat sinks. Then heat sinks are made with either which material we have to use for heat sinks. Either copper or aluminum. Copper or aluminum you have to use. But which is the economical? Aluminum is the economical. Like this also you can expect the question. Aluminum is the economical. Yes. Then which is the economical strength? This aluminum is the economical. Then this one more protection scheme is there, gate protection. What is the purpose of using gate protection? In the total SCR, gate is very sensitive element. To protect the SCR gate, we are using gate protection scheme. Then what is the purpose of using this R2 SCR? To protect the SCR gate from the overcurrents. I will write here gate protection. In gate protection scheme, for the purpose used. This I am writing in a gate protection. A separate protection scheme is employed for the gate terminal. A separate protection scheme is employed for the gate terminal. In this gate terminal, mainly you have to concentrate R2 resistor for the purpose of using R2 resistor. That is overcurrent protection. Overcurrent protection of the gate. Overcurrent protection of gate. Overcurrent protection of gate. We have to use this R. Then, what is the purpose of using GINA diode? The GINA diode. This is the GINA diode. This is the GINA diode. That is over voltage protection of gate. Important. Over voltage protection of gate. Over voltage protection of gate. Over voltage protection of gate. Okay, that is the purpose of using GINA diode. Then one more is, what is the purpose of using this RC filter? This I am using to bypass high frequency noise signals. Or to bypass high frequency noise signals. High frequency noise signals. Like this, you can explain about the protection scheme. Noise signals. To bypass high frequency noise signals, this protection scheme is employed. Clear? Yeah, this about the protection of the SCR. If the question is asked related to protection methods, you can explain like this. Next. As a summary for this question, increasing, yes, just a minute. Yes, friends. Yeah. Here, this slide at the end I will explain. This slide I will explain at the end. One more type of model of question that is asking students. MOSFET switching losses in high frequency pump control. MOSFET switching losses in high frequency pump control. This is important. Application point of view. In high frequency pump control, like in BLDC motor control, then in a permanent magnet synchronous motor drives, MOSFETs switch at high frequency switching. At high frequency, switching loss increases with frequency, affecting the efficiency and thermal performance. It affects the efficiency, it will affect performance, thermal performance also. The question is asked like this. Based on this one, how the question is asked. Plot the switching losses versus frequency. Explain like this. You already know that if the frequency increases, the switching losses also increases. Then this is the switching losses form. Half into VDS, ID, TR plus TF, FSW. This is the switching frequency. TR is the rise time. TF is the fall time. Fall time. Then FSW is the switching frequency. Switching frequency. For this question, this is the answer. If the question is asked, plot the switching losses versus frequency, we know that if frequency increases, switching loss also increases. Switching losses increasing with frequency. Important. At a very high frequency, the switching losses dominates the total losses. The switching losses are more dominant as compared to total losses also at a high frequency switching. And one more question. Can you draw the efficiency versus frequency curve? Efficiency versus frequency curve. For same type of model, if the question is asked, plot efficiency versus frequency, then we know that if frequency increases, what are the switching losses? Frequency increases, the switching losses are increases. If switching losses are increases, what are the efficiency going to decrease? That's the reason why if the frequency is going to increasing, the efficiency is going to decreases. Why efficiency is going to decreasing, students? Why the efficiency going to decreases? Because losses are increases. Because losses are this one. Efficiency is high at low medium frequency. Efficiency drops at high frequency due to increased switching losses. Why the efficiency is going to decreasing at high frequency? Important curve. The question is asked, plot the efficiency versus frequency curve. We can plot like this. Next. The same related, one more model of questions. Trade-off between the size and efficiency. Then what is the compromise between the size and efficiency? High frequency, smaller size. We know that. High frequency devices are the smaller size. But high frequency, lower efficiency. See the trade-off between the size and efficiency steps. If you have to design the small size of devices, you must design for high frequency. But if you design for high frequency, efficiency is going to reduce. That's why for small size, small inductors and capacitors, higher power density, smaller motor size is possible, better dynamic response. But the problem is, if you select the high frequency, small size, all these are advantages. Smaller inductor and capacitors are enough. Higher power density is possible. Smaller motor size is possible. Better dynamic response is also possible. But what are the problems? Switching loss will increase us. Higher heat dissipation. Needs larger heat sinks and cooling requirements. Reduced overall efficiency. This is the trade-off between the size and efficiency. If the question is asked like this, can you explain the trade-off between the size and efficiency? Yes, sir. Yes. When frequency increases, size will reduce us. But problem is, when frequency increases, efficiency is going to reduce. That's why optimal frequency is a compromise between size and efficiency. That's why don't design for very high frequency. You have to select the optimal frequency. Select the frequency in such a way that we can get the maximum efficiency. Beyond that, don't design for high frequency. This optimal selection of the frequency is enough to compromise between the size and the frequency, size and efficiency. To compromise between the size and the efficiency. This is also very important. Trade-off between the size and the efficiency. Next, one more possibility of question that is asked. That is why thermal runaway is possible in the case of MOSFETs. Generally, point to remember, friends. Thermal runaway is exist in the minority carrier devices. In majority carrier devices, thermal runaway is negligible. Majority carrier devices, thermal runaway is negligible. But even though MOSFET is a majority carrier device, there is a thermal runaway in extreme cases. What is that extreme case? Why thermal runaway is possible? MOSFET losses, especially switching losses, produce heat. If there is a very high frequency switching losses, junction temperature will increase. Then, once the junction temperature is increases, then its on-state resistance is increases. Conduction losses increases. More heat is generated. Positive feedback loop can occur if cooling is insufficient. Then leads to thermal runaway in device failure. Then because of this thermal runaway, device failure. What do you mean by thermal runaway? Cumulative increase of temperature. Because of the high switching losses. Because of high switching losses or high conduction losses. If the conduction losses in the MOSFET is increases, if conduction losses, that is, if temperature will increases, on-state resistance will increases, conduction losses will increases, heat is increases, again temperature increases, again temperature is increases. This will cumulate to increase of temperature. Cumulate to increase of temperature. Increase of temperature. Yes, friends. Once again, I am repeating. Generally, thermal runaway is exist in the minority carrier devices, not in majority carrier device. But even though MOSFET is a majority carrier device, in some extreme cases, thermal runaways exist. When? If it is operated at high frequency. Because of high frequency, switching losses will increases, temperature will increases, on-state resistance will increases, then conduction losses will increase. If the conduction losses will increases, again temperature increases. Again conduction losses will increase. Again temperature will increase. It leads to thermal runaway. That's the problem. That's why excessive temperature performance degradation, thermal runaway, device will fail. Because of this thermal runaway, the device is failure, even it causes the permanent damage also. Because of that high temperature revision, the device is permanently damaged. That's why. Does thermal runaway occur in MOSFET? Thermal runaway in MOSFET is less severe than in BJT due to positive temperature coefficient. But it can still occur under high frequency switching and poor thermal design. This is important. If you are not providing proper cooling, if you are not providing proper heat sink arrangement, then that is a poor thermal design. Poor thermal design in the sense we are not providing proper cooling arrangement, proper heat sink arrangements. Then there is a thermal runaway. Okay, this point to remember. Generally, thermal runaway is less severe in normal cases in the case of MOSFETs. But BJT is more, that is more subjected to thermal runaway. But MOSFET normally there is no thermal runaway. But in extreme cases, in these cases only, there is a possibility of thermal runaway. Okay, that you have to concentrate. Then finally, this I am going to explain this slide. This is the final slide. Then summary I am going to give here. Increasing frequency reduces size but increasing switching losses. Reducing efficiency and increasing thermal stress. Proper design avoids thermal runaway and ensures reliable high frequency operation. That's why proper design is required. Optimal frequency is a compromise between size and efficiency. Therefore, design tips for high frequency pump control. Finally, this is high frequency pump control now. Use optimal switching frequency, proper thermal management, cooling arrangement. Proper thermal management in the sense, cooling arrangement. Choose MOSFET with low value of on-state resistance. Minimize parasitic inductance. Then monitor the temperature continuously. This design tips for the high frequency pump control. Yes, friends. In this session, with respect to power semiconductor devices, different models of questions for interview prep that I explained. This is about the session. The next coming session also we will see other models of questions with respect to power semiconductor devices. After that, I will start the chapter 2, that is the rectifier related questions. This is about the session. Thank you. Yes. My dear aspirants, welcome to the session. Welcome to Scientist Interview Prep course. for BARC, ISRO, DRDO and NIC. Myself, Surendra Babu, subject Power Electronics. Continuation of different concepts of power electronics for interview prep course. The previous sessions that I discussed most important gunshot models of questions for interview point of view. In this session, I am going to starting one more topic, rectifiers related interview questions. Previous sessions that I given power semiconductor devices related interview prep questions, that is interview questions. Today topic is rectifiers related. Students, all of you, welcome to the session. Welcome to Margadarshan Scientist Interview Prep course. These are the most important gunshot models of questions who are facing the interviews for PSU's point of view, mainly for BARC, ISRO, DRDO, NIC and other central PSUs. All of you, welcome to the session, students. Shall we start? Today topic, rectifiers related questions in power electronics. Yes, friends, all of you concentrate. Chapter 2, that is rectifier AC to DC converters. The first one is the topic in rectifiers is application oriented question. Pump plus rectifier driven irrigation system in rural India case. From this application oriented also, the questions are asking in interview for different PSUs. Pump plus rectifier driven irrigation system is, this is the block diagram. The question is asked, can you draw the pump plus rectifier driven irrigation system block diagram? Then you have to make the, here again two cases. The question is asked based on the uncontrolled rectifier or controlled rectifier. Here the question is asking for by using the uncontrolled rectifier, single phase uncontrolled rectifier. Here uncontrolled rectifier, you have to take the bridge rectifier, diode bridge rectifier. They don't mention half wave rectifier like that now. Generally you have to take the full wave rectifier only. It's uncontrolled rectifier, that's why I taken the diode bridge rectifier. The output of the rectifier is DC. Then that is connected to the DC motor. Then pumping the water, that water to field. Okay. This is the block diagram representation of pump plus rectifier driven irrigation system. This is mainly rural India case. This block diagram is using uncontrolled rectifier. The question is asked uncontrolled rectifier, then use uncontrolled rectifier. If they ask the controlled rectifier, use the, that is single phase, full wave or fully controlled rectifier. That question is also there, that you will see. This is the first question is, the first topic is related to pump plus rectifier driven irrigation system using the uncontrolled rectifier. That is single phase uncontrolled rectifier feeds a DC motor pump drawing water from a borewell. This application oriented questions are framed in PSUs. Yes, friends. Then after drawing this one, mainly they will ask one question is with respect to which is the circuit diagram. This is the circuit diagram. Can you redraw the circuit diagram separately? Yes. You draw the circuit diagram separately like this. This is the single phase, that is uncontrolled bridge rectifier. Single phase uncontrolled bridge rectifier. The single phase uncontrolled bridge rectifier. The output of the rectifier is given to the motor. Or we can also draw like this. This output of the this output of the rectifier. This output of the rectifier is given to the motor. This output of the rectifier is given to the motor. Now the load is the motor load here, DC motor load. DC motor load. In DC motor there is a back EMF. EB is the back EMF. RA is the armature resistance. LA is the armature inductance. This is the question we can expect. Can you draw the circuit diagram separately? Then you draw like this. The output of the rectifier is given to the DC motor. Then this is the output of the rectifier. It is the input voltage of the motor, that is the armature voltage. The input voltage of the motor is nothing but armature voltage. This is the armature resistance and this is the armature inductance of the motor, and this is the back EMF. Sometimes they will ask the question, can you explain the operation? Then you know that positive half cycle D1, D2 will conduct, negative half cycle D3, D4. If they ask the, can you explain operation? You have to explain operation like this. Then positive half cycle, which devices will conduct? Positive half cycle D1, D2 will conduct. D1, D2 conduct. Negative half cycle D3, D4 conduct. Okay. But in application point of view, how the questions are asking, that is important. D3, D4 conduct. That is, load is subjected to unidirectional voltage and unidirectional current. Always current is in one direction only. Load is subjected to unidirectional voltage or unidirectional current. But what about the source? Source is subjected to bidirectional voltage or bidirectional current. That is, if D1, D2 is conducting, through source current is flowing this direction. Then if D3, D4 is conducting, through source current is flowing this direction. That's why source is subjected to what nature of current? Source is subjected to bidirectional nature of current. This is source is subjected to bidirectional. Source is subjected to bidirectional. So, bidirectional current. This is important. First, they will ask what is the total system block diagram, what is the circuit diagram, and in this circuit diagram, one more question we can expect. Can you write the what is the average output voltage for this case? It is a single phase full wave diode rectifier. For a single phase diode rectifier, the average output voltage is equal to 2 Vm by pi squares. Yeah, this is the average output. Then, if they ask what is the RMS output voltage, the RMS output voltage is equal to Vm by root. RMS output voltage is equal to Vm by root. That also you have to concentrate. And one more question we can expect like this. In this circuit, if any one diode is damaged and open circuited, then this circuit acts as a which one? It acts as a half wave rectifier. If any one diode is damaged and open circuited, it acts as a half wave rectifier. Yes, friends. If any one diode is damaged and open circuit, then how it acts? It acts as half wave rectifier. Half wave rectifier. Then in that case, what is the average output voltage? Then you have to write average output voltage equal to Vm by pi. If the question is asked, can you write what is the RMS output voltage? This is equal to Vm by 2. Yes, friends. Then most important, already what type of questions are it is framed? This one. This one question is framed. Draw input current waveform. Is it sinusoidal? Is it a sinusoidal? Like that question we can expect. Yes, sir. If you want to draw the input current waveform, here the question is asking input current waveform. Here to draw the input current waveform now, you have to consider the back EMF also. By considering the back EMF, here in a DC motor, by considering the back EMF current, this is the back EMF, back EMF voltage. This is by considering the back EMF. Now I am drawing the current waveform. Current waveform. Students, we know that positive half cycle D1, D2 will conduct, negative half cycle D3, D4 will conduct. Can you draw the current wave? Then we can get the current waveform like this. If you draw the current waveform, what type of current waveform we can get? This I am drawing this current waveform. Here the question is asking input current waveform, not output current waveform. It is the input current waveform. This is the input current waveform. If supply voltage exceeds the back EMF, then only diodes will conduct. If the supply voltage exceeds the back EMF, then only diodes will forward bias, then diodes will conduct. Here, supply voltage greater than the back, that is the back EMF voltage, then only diodes will conduct. Positive half cycle, which device will conduct? D1, D2 will conduct. Here D1, D2 conduct. We can get the current waveform like this. D1, D2 current. Then here which devices will conduct? D3, D4 will conduct. D3, D4 will. We know that source is subjected to input current waveform. Here it is asking that input current waveform or source current waveform. Source is subjected to bidirectional current. Source is subjected to bidirectional current like this. It is not a output current waveform. This is the source current waveform. Here which diodes are conducting, students? D1, D2 is conducting. Here which diodes are conducting? D3, D4 is conducting. Again D1, D2 is conducting. Again D3, D4 is conducting. That is the output, the source current, not the output current waveform. Here it is an input current waveform. This input current waveform or source current waveform. Source current waveform. Input current waveform or source current waveform. Correct. This input current waveform or source current waveform is not completely sinusoidal. The waveform is distorted. This waveform is not completely sinusoidal. The waveform is distorted. Then because of distortion of the waveform, there is harmonics are present at input side. There is harmonics are present at input side. Therefore, presence of harmonics at input. Here the question is asking, draw input current waveform. Is it sinusoidal? No, it is not sinusoidal. It is not sinusoidal. Not sinusoidal. Then input current, it consists of harmonics. It consists of harmonics. It consists of harmonics. That is, current flows only when instantaneous AC voltage exceeds the back EMF. That I told now. The instantaneous voltage exceeds the back EMF, then only current will flow. This is the back EMF voltage level. I am assuming that this is the back EMF. If this instantaneous voltage is more than the back EMF, then only the current will flow. This instantaneous voltage level is more than the back EMF, then only the diodes will conduct, current will flow. The instantaneous voltage level is more than the back EMF, then only current will flow. The instantaneous voltage level is more than the back EMF, then only current will flow. But this is the input current waveform that I told students. If D1, D2 is conducting, how the current will flow? With respect to source, it is asking. With respect to source, if D1, D2 is conducting now, this is the current flow, direction of current. The current flow like this. If D1, D2 is conducting, with respect to source, it is upward direction. If D3, D4 is conducting, students, if D3, D4 is conducting now, if D3, D4 is conducting, the current flow like this. This is the path for if D3, D4 is conducting. Then the current will flow in the downward direction. That's why source is subjected to what nature of current? That is the bidirectional nature of the current. Bidirectional nature of the current. Like this we can get. Therefore, the current is not a sinusoidal. Current is not sinusoidal. It is pulsating, discontinuous and highly distorted. It is a discontinuous, highly distorted waveform. Conduction in each half cycle through a pair of diodes. Conduction in each half cycle through a pair of diodes. D1, D2, one pair of device is positive half cycle. D3, D4, one pair of device is negative half cycle. That is, in each half cycle, one pair of devices will conduct. In this topic, the question is asked like this, students. Can you draw the input current waveform? Yes, you draw the input current waveform like this. Is it a sinusoidal? No, it is not a sinusoidal. Then it is a distorted waveform. Once it is a distorted waveform, it consists of harmonics. It consists of harmonics. Then continuation of this, then what type of question we can expect? Yes, friends. Can you draw the input current versus time and harmonic spectrum? That is, input current versus time and harmonic spectrum. That is, plot input current versus time and identify the harmonic content. Yes, we know this. In the case of input current waveform, it is the input current waveform. Same input current waveform I am drawing. What type of input current waveform you got? This is IS. Then I got the input current waveform like this. I got this is the input current wave. Once again, same question, but here it is asking that harmonics. I got the input current waveforms. Like this, I got the input current wave. This is the source current. Here, which device is conducting? D1, D2 is conducting. Here, which diodes are conducting? D3, D4 is conducting. Here, which diodes are conducting? D1, D2 is conducting. Here, which diodes are conducting? D1, D2 is conducting. This is omega. Like this, we have to explain. See, in this same question, sometimes how to calculate this angle theta? Theta. It is the minimum angle at which diode starts the conduction. Can you calculate this theta? Yes, theta equal to sin inverse EB by Vm. Sin inverse EB by Vm. This angle is because of the back EMF. Because of the back EMF, it is going to discontinuous. Okay. This is the minimum angle at which diode starts the conduction. Theta is the minimum angle at which diode starts the conduction. Theta equal to sin inverse EB by V. You have to take either theta 1 also. This you have to take the theta 1. Theta 1 equal to sin inverse EB by Vm. Okay, this is important. This is theta 1 and this angle is taken as a theta 2. Theta 2. And this side also symmetrical. This is a symmetrical waveform. This also taken as a theta 1. If they ask what the relation between theta 1 and theta 2. But point to remember students, here theta 1 plus theta 2 equal to 180 degrees. Theta 1 plus theta 2 equal to 180 degrees. Then theta 2 equal to 180 minus theta 1. Okay. This also you have to explain if they ask the question. That is in this D1, D2 is conducting how much angle? Theta 1 to theta 2. How much angle D1, D2 is conducted? That is each diode conduction angle. For this case, each diode conduction angle. Each diode conduction angle. If they ask what is the each diode conduction angle, then each diode conduction angle you have to take the theta 1 to theta 2, that is theta 2 minus theta 1. The conduction angle equal to theta 2 minus theta 1. Theta 2 minus theta. What is theta 2? 180 minus theta 1. If you want substitute here, then what is the conduction angle? 180 minus 2 theta 1. Then how to calculate theta 1? Apply this formula here. What is the Vm? Maximum value of supply voltage. EB is the back EMF. What is EB here, students? It is a back EMF. Like this we can expect the questions. Okay. Now the question is asking input current versus time. Yes, it is input current versus time. Input current is nothing but a source current. This is the input current versus time curve. Then what is the harmonic spectrum? If you apply Fourier analysis for this waveform, now if you apply Fourier analysis for this waveform, Fourier analysis. If you apply Fourier analysis for this waveform, then it consists of fundamental plus harmonic. Fundamental plus harmonics. It consists of fundamental plus harmonics. Why these harmonics are introduced? Because of the waveform is distorted. Because of the waveform is distorted, it consists of fundamental plus harmonic. Which harmonics it consists of? Third harmonic, fifth order harmonic, seventh order harmonic, and so on. Then which is the dominant harmonic? The dominant harmonics are this one. Third, fifth to seventh. Third, fifth to seventh. It also consists of ninth order harmonic. Ninth order. Ninth and so on. 11th order, 30. It consists of only odd harmonics. Only odd harmonic. Fundamental plus harmonic. Then which are the dominant harmonic? These are the third order, fifth order, and seventh order harmonic. What the frequency of third order harmonic? The third order harmonic frequency is how much? If it is asked, 3f. What the frequency of fifth order harmonic, friends? The fifth order harmonic equal to 5f. What the frequency of seventh order harmonic? You have to take the 7f. seventh order harmonic equal to 7f. That is the frequency. Then which is the dominant harmonics? This is the harmonic spectrum. Harmonic spectrum is, that is, the dominant is which harmonic? This is the fundamental. This is the fundamental. Fundamental is not a harmonic. This is one of the frequency component. But which are the harmonic? Third order is harmonic, fifth order is harmonic, seventh order is harmonic, ninth order, 11th order, 13th order, and so on. Then which is the dominant harmonic here? Third, fifth, and seventh. Which is the most dominant harmonic? Third order students. In this waveform, if the question is asked, which is the most dominant harmonic? Come on, sir. Most dominant harmonic. The most dominant harmonic is which one? This is the third order. Most dominant is third. Dominant is third, fifth, seventh. Most dominant harmonic is third order. What the frequency of third order? 3f. If fundamental frequency equal to 50 Hz, if f equal to 50 Hz, students, what the third order harmonic frequency? 3 into 50, 150 Hz. What the fifth order harmonic frequency? That is 5 into f, 5 into 50, 250 Hz. What is the seventh order harmonic frequency? 7 into 50 strings. That is 350 Hz. Clear? Okay, like this you have to answer. What the order of harmonics? Then which is the dominant harmonics? Which is the most dominant harmonic? This is input current versus time and harmonic spectrum. Like this you have to explain. Plot input current versus time and identify the harmonic component. This is the concept you have to apply. Explain, students. Next. For the same concept, one more question. How does distorted current affect the transformer heating? How does distorted current affect the transformer heating? Concept very simple, students. We already know, because of the distorted waveform. This waveform is a distorted waveform. That I told already. It is a distorted waveform. It is a distorted waveform. It is a non-sinusoidal. It is a distorted waveform. This is the distorted waveform. Yes, friends. Because of the distorted waveform, there is harmonics are present. Then because of the harmonics, then what happened? Losses will increase. When the losses will increases, what is the temperature? The temperature also increases. Distorted current causes additional losses in the transformer. Distorted waveform causes the additional losses in the transformer. The copper losses will be increases due to higher value of RMS current. Copper losses are increases because of the higher values of RMS current. Eddy current losses also increases because we know that eddy current losses are proportional to frequency square. W equal to K into B maxima square F square T square formula. You know, in this W equal to K into B maxima square. Yes, friends. F square T square. What is B maxima here? Maximum flux density. What is F here? Frequency. What is T here? Lamination thickness. Thickness of lamination. That you know in mission subject. That is electrical mission transformers mainly. That is the frequency increases. If the frequency is increases, but the eddy current losses increases. When the eddy current losses are increases, hysteresis, then there is slight increase in the hysteresis losses and eddy current losses. When the hysteresis losses and eddy current losses increases, what the core losses? Core losses also increases. Then copper losses are increases. Yes, friends. Copper losses are increases in a transformer. Iron losses are increases. Then what are the total losses in a transformer? These are the major losses. The total losses in a transformer is increases. Then if the total losses are increases, what the temperature is also increases. The temperature rise is also increases. This is the problem. This is effect of distorted current on transformer heating. Because of the distorted waveform, the transformer is more heating effect. The transformer is subjected to more heating effect. The reason is like this you have to explain. That is extra heating. Whenever losses are increases, reduced efficiency, then overloading problem, insulating aging, that is the insulation will be damaged, then reduced life. The transformer life will be reduced. We can't use the transformer for more time. That is, we can't use this transformer for a long time. That is the problem. That's why, because of the distorted waveform, because of the transformer is subjected to distorted waveform. Input current waveform is, that is the current passing through the transformer windings only. Because of the distorted waveform, extra heating effect, reduced efficiency, overloading effect, insulation aging, then insulation will be damaged, then reduced life. We can't use the transformer for long life or long run. Yeah, that is the problem with the effect of distorted current on a transformer. This one more question, friends. All these questions with respect to this topic on related to this topic, what type of questions it is framing. This is the topic. What the topic I taken, friends? It is rectifier related. Pump plus rectifier drive irrigation system. This is a rural India case. Based on this, how the questions are asking, that I am explaining. That is. Can you draw the input current waveform? Yes, you draw the input current waveform. Can you explain input current versus time and harmonic spectrum? What harmonics it is present? That you have to explain. What is the effect of distorted waveform on a transformer heating? Because of the distorted waveform, extra heating effect, reduced efficiency. Why efficiency is going to reducing? Because of more losses. The losses are increases now. What is the efficiency, students? The efficiency is going to decrease. Correct? If losses are increases, what is the efficiency, students? The efficiency is going to decrease. That's the problem. Clear? That you have to concentrate. Next. In the same model, in the same topic, one more question. How the question is asked? Important. This is also application one. If water demand fluctuates, how does motor torque ripple behave? If water demand is fluctuates, how does motor torque ripple behave? Motor torque ripple behave. Students, we know that the DC output voltage of rectifier has a ripple voltage. The DC output voltage is ripple voltage. Now we know that the output voltage of the rectifier is given to the motor. Then what is the motor ripple volt? Then here it is uncontrolled rectifier. Now this uncontrolled output voltage is like this. What is the output voltage of uncontrolled rectifier? Like this we are getting. This is the output voltage of the uncontrolled rectifier. Then it consists of more ripple voltage. More ripples. If voltage is ripples, then armature current is also ripples. Then armature current is also ripple. Armature current also ripple. Because of voltage is ripple, armature current is also ripple. If armature current is ripple, we know that T is proportional to pi Ia. Na? If it is ripple in nature, torque is also more ripple. Therefore, torque is proportional to pi Ia, then hence torque is pulsating. Simple explanation. Now, if output voltage is ripple, then output current. The output current of the rectifier only is given to motor. Na? The output current of the rectifier only given to the motor. The motor current is nothing but which one? Armature current. The motor current. See, the output of the rectifier only this one, students. The output of the rectifier only given to the motor. This output current of the rectifier is nothing but armature current. That's why if the output voltage is ripple, output current is also ripple, then armature current is also ripple. If the armature current is ripple, students, what the torque is also in pulsating nature. Torque is also in pulsating nature. Therefore, what are the effects? If water demand fluctuates, how does the motor torque will ripples behave? Then mechanical vibrations. Because of this ripple torque, there is a large vibrations in the motor. Noise in pump. There is some noise in the pump. Because of the harmonics, there is noise is produced in the pump. Wear and tear problem. Reduced life of the motor and pump. Reduced life of the motor and pump. This is Vs and Is1. Vs and Is1. This is the power factor angle. This is angle between Vs and Is1. This is the called fundamental. This is called displacement angle. Actually, pi 1 is called displacement angle. This is the displacement angle. Fundamental current. This is the total current. Fundamental current and total current. This you have to remember. Understand? Then mechanical vibrations, noise in pump, wear and tear, reduce life. Where this is useful? In the next question it is useful. That I will explain. Mechanical vibrations, noise in pump, wear and tear, reduce life of the motor. That is because of the ripple voltage, ripple current, ripple torque, pulsating torque. Because of the pulsating torque, mechanical vibrations, noise in the pump, wear and tear problem, reduce life of the motor and pump. Yeah, this is the problem with motor torque ripple. That is, if water demand fluctuates, how does motor torque ripple behave? Torque will be fluctuate. Torque will be pulsating. If the torque is pulsating, all these are the effects. If the torque is pulsating now, these are the effects on the motor. That you have to concentrate. For the same topic, one more question. What happens to the power factor? This waveform, this phasor diagram, this useful here. Okay. What happens to the power factor? What happens to the power factor? Then we know that the fundamental formula for power factor is given by displacement factor by displacement factor into distortion factor. Input displacement factor into distortion factor. This is the input power factor. Your power factor is nothing but input power factor. Then this is the fundamental current. This is the fundamental. You have to take IS1, fundamental value of source current, and this is the total source current. But we know that power factor equal displacement factor in distortion factor. Then displacement factor is less than 1. Distortion factor is also less than. Displacement factor is less than 1. And distortion factor is also less than. In this case, because of displacement factor is less than 1, distortion factor is also less than 1. Hence, power factor becomes very low. When the power factor becomes very low, that is in the range of 0.6 to 0.7. That is what the power factor impact. The power factor is given by displacement factor into distortion factor. Because of the distortion of the waveform, the power factor becomes very low. It is in the range of 0.6 to, typically in the range of 0.6 to 0.75. Typically in the range of 0.6 to 0.75. Okay, this is the problem. The question is asked, what happened to the power factor? The power factor will be reduced. Why the power factor is reduced? Because of the distortion factor effect and displacement factor effect. Because of the distortion factor and displacement factor effect, the input power factor is going to reduce. Then it is in the range of 0.6 to 0.75. This is also one more question with the same topic. Next. Okay. Generally, in the case of uncontrolled rectifier, we are getting the ripples at the output side. If the question is asked like this, how would adding a filter capacitor change the wave? This is the ripple voltage. Generally, ripple voltage we are getting like this. This is ripple voltage. This is the ripple voltage. This is the ripple. This ripple voltage I drawn with respect to average line. This I taken. That is, without filter capacitor, the output voltage of the rectifier is high ripple, high torque ripple, poor motor performance. Concept very simple, sir. The output of the rectifier is given to the motor. Now what I am telling, this output of the rectifier is having more ripple. Because of more ripple voltage, more ripple current. Because of more ripple current, torque is also more ripple. If torque is always fluctuating, then motor performance is not good. If you connect the filter, because of the filter capacitance, the ripples will be reduced. Due to filter capacitor, ripples will be reduced. Ripple voltage is reduced. If ripple voltage is reduced, torque ripples also reduced. Smoother motor performance. Then the performance of the motor will be better. This question is important. The question is asked, okay, you are telling that in the output of the rectifier, there is a ripple voltage. Because of ripple voltage, there is a ripple current. Because of ripple current, there is a ripple in the torque. Because of ripple in the torque, there is vibrations in the motor. There is a noise in the pump. That problem you are telling. Now, if they ask the question like this is the cross question. When I connect the capacitor at the output of the rectifier, what happened? Yes, the motor performing somewhat better, improvement, smooth operation. Because the ripples are going to reduce. Ripples not completely eliminated, but ripples are going to reduce it. Somewhat better performance as compared to without filter capacitor. With the filter capacitor, the motor performance will be increased. Then the noise will be reduced. Noise in the pump is reduced. Vibrations in the motor will be reduced. That like this you have to answer, students. Okay, all these questions with respect to, that is, water pump, that is rectifier. This question, students. Once again I am showing this question. pump plus rectifier driven irrigation system. This is a practical application point of view. In this topic, all these models of questions it is asking. All these models of questions is asking in different PSUs interviews point of view students. That you have to concentrate. Then with the filter capacitor, can you draw the input current waveform? Yes, this is the input current waveform. With filter, this is positive, this is for negative. Can you draw the input current waveform for with filter capacitor? Can you draw the input current waveform for with filter capacitor? We can get the with filter capacitor, we are getting the waveform like this. Input current waveform with capacitor. Input current becomes more peaky and flows in short duration near voltage peaks. Yes, this is important. Because of the capacitor, there is some advantage is there, but there is one drawback is there. Because of the capacitor is connected, the input current waveform becomes more peaky. When the input current waveform becomes more peaky, there is higher value of the peak current. Here I drawn with respect to only one pair of devices, D1, D2 or D2. This is with respect to D1, D2, with respect to one pair of devices. With respect to one pair of devices. One pair of devices. Let if D1, D2 is connected. D1, D2 is conducting, we are getting positive current now. Then because of the filter capacitor, input current waveform will change. Then we are getting a more peaky waveform at input current waveform. Then because of the more peaky waveform, the worse power factor. The power factor will going to reduce. More stress on the transformer and diodes, and this is the problem. Because more peaky current now, because of more peaky current carried by the diodes, this more peaky current is carried by the diodes, there is a more stress on the transformer and diodes. There is advantage is there. Motor performance is increasing, but there is a stress on the diodes and transformer. The stress on the diodes and transformers will be increases with the capacitor. With the capacitor, is there any problem? Is there? Yes. This is the problem that you explain. The question is asked. Yes, you are telling that if you connect the capacitor, you are telling that ripples are reducing. Then torque ripples are also reducing. The motor performance is increasing. Is there any drawback? Is there? Yes, it is the drawback is there at input side. At input side, there is a drawback. There is stress on the transformer. There is a stress on the diodes. Sorry. That you have to concentrate. Clear? Then, final summary that you have to concentrate. Input current waveform is pulsating. It is a distorted waveform without filter capacitor. With the filter capacitor, more peaky, very narrow pulses. Harmonic content, third order, fifth order, and seventh order. Even higher order due to narrow pulses. There is higher order harmonics are present due to narrow pulses. But here low order harmonics are present, higher order harmonics. Higher order harmonics are less effective as compared to which is the most dominant harmonics. Low order harmonics are the more dominant harmonics. Power factor is 0.6 to 0.75. Worse, this is important. Because of the capacitor, the input power factor is again going to reducing very less power factor because of more peaky waveform. Transformer heating high, very high due to high peak current. See, motor performance is increasing because of the capacitor. Output side performance is increasing, but input performance is going to decreasing here. Input performance is a very worst performance at input side because the capacitor is connected at output side. Output DC voltage ripple high, low. These ripples are very low with filter capacitor. Motor torque ripple high. Motor torque ripples are good performance at output side, then poor performance at input side because of the filter capacitor. Remember, motor performance poorer, vibration, noise, wear and tear. Better, smooth operation. Stress on diodes moderate, high due to peak current. The stress on the diodes will increase. This is the summary with respect to the topic, that is application oriented topic that I started now. That is important, that you have to concentrate. Then final conclusion. Rectifier with DC motor pump draws non-sinusoidal current from AC supply. Yes. Harmonics cause extra losses, transformer heating and poor power factor. Torque ripples occurs due to pulsating DC current, mechanical issues. Filter capacitor improves the DC output and torque but worsen input current waveform. See, if you connect the capacitor at output side, yes, torque waveform will be improved, but problem is input current waveform and power factor. Then input current is non-sinusoidal, rich harmonics, heating and poor power factor. Torque ripples due to pulsating DC. Capacitor improves output but increases input stress. Poor performance at input side. Good performance at output side because of the capacitor. Can you accept this? Yes. Because of the capacitor. Poor performance at input side but better performance at output side. Clear, students? This you have to accept. Okay. This one of the application oriented question. In this application oriented question, how many number of questions it is framed? Like that you have to concentrate. Only one application I taken. Pump drive using the uncontrolled rectifier. How the questions are framed. Like this you have to answer. Clear? Okay. I am taking one more application oriented question. This also framed different PSUs. Thyristor controlled water flow system. Thyristor controlled. Previously I taken uncontrolled rectifier. Now thyristor controlled water flow system. That is AC supply, SCR controlled rectifier, DC pump motor. Thyristor controlled water flow system. Can you draw the system diagram? Yes. Thyristor controlled water flow system. Simply you take like this, friends. Uncontrolled rectifier means you take the diode bridge rectifier. Unless otherwise specified, you go through with diode rectifier only, bridge rectifier. Here also SCR controlled rectifier they given. It is not given, it is half wave rectifier, semi converter like this. If it is not given, you take the full wave rectifier. Then it is a fully controlled rectifier. This is the diagram I am drawing. It is a fully controlled rectifier. It's a thyristor control. Yes, friends. You draw like this. Take the full wave rectifier or fully controlled rectifier. Armature resistance, armature inductance. This is the DC pump motor. DC pump motor, and this is the back end. Yes. The input voltage is equal to Vs equal to Vm psi. Yes, this is T1, T3, T4, T2. Then we know that in this case T1, T2, T3, T4. Positive half cycle T1, T2, negative half cycle T3, T4. Positive half cycle, which devices will conduct? T1, T2 conduct. How much angle it will conduct? That depends on the load. T1, T2 conduct. Negative half cycle, T3, T4 conducts. Okay. This is the thyristor control water flow system. This DC motor, this is the motor where EB is the back EMF, that IA is the armature current. This is the I0. The output current of the rectifier is input of the motor. For this case, if they ask, can you write the average output voltage formula? Yes, 2 Vm by pi cos alpha. Unless otherwise specified, you take without freewheeling diode. With the freewheeling diode is a special case. Then what is V0 equal to 2 Vm by pi into cos alpha? If they ask, can you write the formula for average output voltage? The output voltage equal to input of the armature. V0 equal input of the motor. Output of rectifier. This is the concept you have to apply. output of rectifier equal to input of motor. Input of motor. What is the input of motor here? VA, armature voltage. Output of the rectifier equal to input of the motor. What is V naught here? This is the average output. Average output. What is the alpha here? Alpha equal to firing angle. Alpha equal to firing angle or triggering angle. Okay. Can you draw the circuit? Draw the circuit like this. Can you write the formula average voltage? 2V. What is the RMS output voltage here? Unless otherwise specified, you take the continuous mode. The RMS output voltage equal to Vm by root. This is the RMS output. Okay. In a thyristor control water flow system, this, if one question is, can you draw the circuit? Draw the circuit like this. Next. Draw output voltage waveform for firing angle. Draw the output voltage waveform for firing angle. Here it is asking that can you draw the output voltage waveform for firing angle? We can also expect the question, plot average output voltage versus firing angle. Draw the output voltage waveform for firing angle. Okay. You take any firing angle. I am taking this as the output voltage waveform for a firing angle. Yes, friends. For simplicity, I am drawing Vs and V naught on the same axis. Vs, I am drawing the source voltage waveform and output voltage waveform for easy drawing. This is omega. For 2 cycles, I am drawing. If the question is asked, can you draw the output voltage waveform? Let us assume that it is a continuous mode of operation. I am taking this is the continuous mode. For continuous mode. For continuous mode. Then you draw the output voltage waveform for firing. This all of you well known this. In study of theory, all of you well known this. Even in application oriented also, if they ask this question, this type of question is very easy for you. Select some firing angle. Any firing angle you select. This is the firing. For this firing angle, I am right. Simple. Let this is the firing angle. We can follow the symmetrical firing angle curve. This is pi. This is pi plus alpha. This is 2 pi. This is 2 pi plus alpha. This is 3 pi. This is 3 pi plus alpha. Then you can easily join like this. Then this is the output voltage waveform for firing angle. You take any firing angle. I taken this much of firing angle. Or you can increase the firing angle also. No problem. And just you join like this. All these, select the firing angle, join like this. This is the output voltage waveform. On the input voltage waveform, I am drawing the output. Like this icon. Then this is the output voltage. Then this is the output voltage. Now from this, what is your observation you tell? Okay, you taken this is the alpha is the firing angle. If you increase the firing angle, what is your observation? If the question is asked like this. If you take this much of firing angle, then what is your observation? For this value of firing angle. 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 Then if you draw the waveform for that value of firing angle, then I am getting the voltage like this. For different values of firing. Okay, better to take in the next separately I have. Okay. This is for one firing angle. If they ask for different firing angles, draw the waveform for different firing angles. Then simply represent the firing angles. That is enough. This is omega t. For easily drawing of waveform, I am taking the source voltage waveform first. Draw the source voltage waveform. For easily drawing of waveform, I am projecting like this. I am projecting like this. Okay. Can you take the firing angle is this one? Can you consider this much of firing? Previously I taken this one. You take this much of firing. This is alpha. For every half cycle also take the firing angle like this. This is the firing angle. This is the firing. Same firing angle. Symmetrical angle control you have to maintain. Then simply join that one. We can get the waveform like this. Drawing of the waveform for different firing angles are very easy. Like this. I am drawing the waveform like this. I am drawing the waveform like this. Okay. For different firing angles. Okay. If you take this is the alpha less than 90 degrees. This if you take the alpha, this alpha na, this I am taken, this is alpha greater than 90. Alpha less than 90 degrees, if you take the average output voltage is negative. For alpha less than 90 degrees, average output voltage is positive. Because here more negative spikes. The negative spikes are more here, negative. Here which is more, positive is more. That's why alpha less than 90 degrees, V0 is positive spikes. Alpha less than 90 degrees, V0 is positive. Alpha greater than 90 degrees, V0 is negative. Why? If you take V0 equal to, what the average output voltage formula students? 2 Vm by pi into cos alpha. Is it 2 Vm by pi into cos alpha? Okay. Then if you take alpha less than 90 degrees, in this substitute any alpha less than 90 degrees, we are getting V0 positive. What is V0 equal to? If you substitute alpha greater than 90 degrees. If you write for alpha greater than 90 degrees, what the V0 you can get? Negative we can. For alpha equal to 90 degrees, important observation. For alpha equal to 90 degrees, V0 0. For alpha equal to 90. Here only question is asked, draw the output voltage waveform with respect to firing angle. Then that is the answer. Just draw the waveform. Next. Same thyristor control pump drive. One more question it is asking that. Plot average output voltage versus firing angle. How to draw the average voltage versus firing angle? What is V0 equal to? 2 Vm by pi into cos alpha. Here it is asking that can you draw the plot? Can you plot V0 versus alpha? V0 versus alpha. Yes. I am asking this. You have to draw for V0 versus alpha. Plot like this. Average output voltage versus firing angle. Average output voltage versus firing. Okay. Alpha is the firing. Yes, can you substitute alpha equal to 0? What is V0 you can get? V0 equal to 2 Vm by pi. Alpha 0, 2 Vm by pi. Alpha equal to 90 degrees friends. What is V0? 0. Alpha equal to 180 degree. What is V0? Alpha equal to 180 degree. What is V0? Cos 180 minus 1. Minus 2 Vm by pi. Now, for different values of firing angles, I am drawing here. Alpha equal 0 degree. For 30 degree. 60 degrees friends. 90 degree. 120 degree. 150 degree. Then 180 degree. Then we can get the output voltage waveform with respect to firing. This type of characteristics we can. This is alpha equal 0 degrees. What is this value? 2 Vm by pi. Alpha equal to 180 degrees. What is this value, friends? Minus 2 Vm by pi. Alpha equal to 180 degrees na. This is minus 2 Vm by pi. This all of you well know this waveform also. This is for alpha equal to 90 degrees na. V0 equal to 0. Then one more observation, friends. Always in a rectifier, current is always positive. Current never be negative. But in a full wave rectifier, voltage is either positive or negative. Voltage is either positive or negative. This quadrant operation also important. Sometimes they will ask the question quadrant operation. V0 positive, I0 positive first quadrant. Then V naught negative, I naught positive. That is, in rectifier, current never be negative. Sir, why current never be negative in the rectifier? Always current is unidirectional. Why? See this one. This is the rectifier. Na? Current always flow this direction only. Current will not flow like this. Na? Current will not flow like this. This is wrong. That's why I naught negative is wrong. Always current is unidirectional. But voltage may be positive or negative. Current negative means we have to allow the current in the reverse direction of the SCS. That is meaningless. Understand? That's why in the case of rectifiers, voltage is either positive or negative based on the type of rectifier. In a full wave rectifier or fully controlled rectifier, this is which rectifier? Full wave or fully controlled rectifier. Full wave, yes, fully controlled rectifier. It is a single phase. Fully controlled rectifier. In a single phase full wave or fully controlled rectifier, voltage is either positive or negative. Current is always positive. When voltage is positive for alpha less than 90 degrees. This is for alpha less than 90 degrees. When voltage is negative, this is for alpha greater than 90 degrees. This is for alpha less than 90 degrees. That's why for alpha less than 90 degrees, this is positive. For alpha greater than 90 degrees, it is a negative. That's why for alpha less than 90 degrees, friends, it is a rectifying mode. It is a rectifying mode. For alpha greater than 90 degrees, it is a reverse braking mode. Reverse braking, important. It's a reverse braking mode. Alpha greater than 90 degrees, it is a reverse braking mode. Then it acts as a, this is the reverse braking mode now. Alpha greater than 90 degrees, V naught is negative, I naught is positive. Then what is the power? Power is negative. Power negative means power is delivered from load to source. Here, alpha less than 90 degrees, friends, V naught positive, I naught positive. Then what is the power? Power is also positive. If the power is positive, power is delivered from source to load. Important. That's why a rectifier, a single phase full wave or fully controlled rectifier is a how many quadrant converter? 2 quadrant converter. Quadrant operation also important. It is used for rectifying mode. It is used for reverse braking mode. Reverse braking mode, power is delivered from load to source. Rectifying mode, power is delivered from source to load. But here the only question is asked. If they ask the cross question like this, can you explain the quadrant operation? Then explain like this. For quadrant operation. What this indicates? Alpha equal to 90 degrees. This alpha equal to 90 degrees. Now, this line indicates alpha equal to 90 degrees. Why? Alpha equal to 90 degrees. What is the output voltage? 0. That's why alpha equal to 90 degrees. Now, this alpha equal to 90 degrees is the boundary between the first quadrant and the fourth quadrant. This is for first quadrant operation. This is for fourth quadrant operation. It is the boundary between the rectifying mode and the braking mode. Boundary between the rectifying mode and braking mode is alpha equal to 90 degrees, friends. Okay, like this you have to explain. This is one question that you have to concentrate. Next, one more important question. How does this affects flow rate? How does this affects the flow rate? If the firing angle is changing, average output voltage is changing. What you are telling that here? If firing angle is changing, output voltage is changing. If firing angle is changing, output voltage is changing. Therefore, how does this affect the flow rate? That is the question is asking. If firing angle is changing, output voltage is changing. How flow rate will affect? How flow rate will affect? Flow rate will affect. This is the question. Concept very simple. We know that V naught equal to VA. The output voltage equal to armature voltage. This armature voltage is nothing but this is the armature voltage. This is the input voltage of the motor. Armature voltage is nothing but input voltage of the motor. This is the input voltage of the motor. This input voltage of the motor, then this armature voltage is proportional to the speed. Armature voltage is proportional to the speed. That speed is proportional to the armature voltage. Firing angle is increases. If the firing angle is increases, the average output voltage is decreases. The average output voltage is decreases. If the average output voltage is decreases, what the armature voltage also decreases. What the speed is also decreases. Speed is also decreases. Then if the speed is decreases, what the flow rate? The flow rate is also decreases. The flow rate is also decreases. You can explain like this, friends. Flow rate Q is decreases. If the alpha is decreases, na, the average output voltage is increases. Then armature voltage is increases. Then speed is increases. Then what the flow rate is also increases. Therefore, by controlling firing angle, this is the effect. By controlling firing angle. By controlling firing angles. Firing angle. The motor flow rate is controlled. By controlling the firing angle, the motor flow rate is controlled. Motor flow rate is controlled. Motor flow rate is controlled. Like this you have to explain. The question is asked like this. How does this affects the flow rate? How does this affects the flow rate? Then by controlling the firing angle, the motor flow rate will be controlled. Next, one more question. At alpha equal to 90 degrees, what happened physically? Why motor may start? This is important. At alpha equal to 90 degrees, what happened physically? Why motor will start? Yes, friends. We know that average output voltage equal to 2 Vm by pi into cos alpha. Na? V0 equal to Vm by pi into cos alpha. At alpha equal to 90 degrees, at firing angle alpha equal to 90 degrees, then what the average output voltage equal to 0. This average output voltage is also denoted as VDC. Therefore, what happened at alpha equal to 90 degrees? Average output voltage becomes 0. Average armature voltage also 0. Why? The average voltage equal to 0, then what the armature voltage is also 0, because the output of the rectifier equal to input of the motor. Output of the rectifier equal to input of the motor. This is the output of the rectifier, students. This is input of the motor. Input of the motor. If V0 is 0, VA is also 0 at alpha equal to 90 degrees. Then motor gets almost 0 average voltage. Then if the motor voltage 0, then pump will stop. There is no voltage from the motor. There is no voltage to the motor. When there is no voltage to the motor, the pump will stop. When the pump will stop, no water flow. No water flow. Then practically small current may flow due to overlap and back EMF. But there is some back EMF. Because of that back EMF, there is small current is exists. Then actually the motor will stop at alpha equal to 90 degrees because there is no voltage. Next. Why motor may start at high alpha? The average voltage is very low. Motor speed will reduce. Once the motor speed will reduce, load torque becomes greater than the available torque. That is, available torque is, the motor torque is less than the load torque. Motor torque is less than the load torque. Motor torque. If the motor torque is less than the load torque, what is the concept? Then motor will stall. The back EMF becomes very small. Then armature current is increases. Why armature current is increases? Ia equal to V minus EB by RA. Then if the back EMF is reduced, what the armature current will increase. Motor overheats and may stall. Because load torque is less than the, that is motor torque is less than the load torque. Na? Because of load torque is more, it draws high current. It draws high current. But because of voltage is reduced, na, the motor speed is reduced. Simple, friends. This current is increases. Then overheats. Overheats. But what happening here? Speed is reducing. Stall. Motor will stall. Motor will stall. Yeah, this is the happening. Why motor may stall? Why motor may stall? Because speed is reduced. Why speed is reducing? This one. Motor torque is less than the load torque. If the motor torque is less than the load torque, then speed is going to reducing. You can explain like this. Is also one of the most important application oriented question for this topic that you have to consider. Next. Therefore, the conclusion points you have to concentrate in this application. Thyristor control rectifier allows the control of average voltage by varying the firing angle alpha. Next. This average output voltage equal to Vm by pi cos. Flow rate of water is proportional to average voltage, that is proportional to cos alpha. That is, we can control the flow rate by controlling the firing angles. Sorry. We can control the flow rate by controlling the firing angle. At alpha equal to 90 degrees, this is the final conclusion point. Average output voltage 0, then pump will stop. At high value of alpha, low speed, high current, motor may stall, motor will overheat also. Then parameter for different firing angles. For alpha equal 90 degrees, that is low alpha, average voltage is high. Sorry. Yes. Yes. At low value of alpha, the average voltage is high. At alpha equal 90 degrees, average voltage is 0. Then at high value of alpha, nearer to 180 degrees, average voltage is 180 degrees. That alpha greater than 90 degrees now. V0 is negative. Next, motor speed. At low value of alpha, high speed, why? Voltage is more. At alpha 90 degrees, it is low and reverse. Because of voltage is negative. Because of voltage is negative, it may be reverse. It is a reverse. Flow rate. At low value of alpha, flow rate is high. At alpha 90 degrees, flow rate 0. At high value of alpha, nearer to 180 degrees, low, and it is a reverse flow rate. Armature current. At low value of alpha, it is a normal. At alpha equal to 90 degrees, it is very low current because of the back EMF. Alpha equal to, this is low due to back EMF, due to EB. This high may be dangerous also because of the negative voltage and back EMF is reduced. Here why? The back EMF is reducing, the armature current is increasing. Motor condition. Low value of alpha, good condition. Alpha equal 90 degrees stops. It may stall or overheat. Alpha nearer to 180 degrees, it may stall or overheat. This is the final conclusion point. Low value of alpha, motor performance is good. Alpha equal 90 degrees, the motor will stop. And high value of alpha, if the question is asked, high value of alpha, motor may stall and overheat. Why motor may stall? Load torque is more than the motor torque. Available torque is less as compared to load torque. Therefore, use freewheeling diode across armature for smooth current. If the question is asked, to get the smooth current, what you have to use? Freewheeling diode. Do not operate at high value of alpha for long time. Why? There is a heating effect, stress. Maintain proper water level and avoid dry running condition. Soft starter, VFD, variable frequency drive is better for large pump motors. What type of drive is preferable? Variable frequency drives are better for large pump motors. Yes, friends? This is about the today's session. In this session, I taken 2 application-oriented questions. In that 2 application-oriented questions, nearly 11 or 12 questions that I explained. See how the questions are asking in different PSUs. These models already framed in different PSUs, central PSUs that you have to concentrate. Whatever you are preparing for interview for different PSUs, these models of questions are important. You have to take the course in Margdarshan Prep. Once we can take the Margdarshan Prep, not only power electronics subject, all the subjects, electrical machines, power systems, all these subjects will detailed explained already what type of models are asked in different central PSUs. With that knowledge, whatever we are providing, this knowledge is enough to answer the any interview question, whatever exam you are facing, students. Okay, this is about the session. The next coming sessions also different models of questions with respect to power electronics. All the topics I explained already semiconductor devices. Now I am explaining for rectifiers. Next coming session also rectifiers. After that I will explain for the chopper related questions. Next inverter related questions. Then next one more important drives related question. AC voltage control and cycloconverter related questions. Then some resonant converter related questions. All these questions that I will explain. This is about the session. Thank you. Yes. Dear aspirants, welcome to the session. Welcome to Scientist Interview Preparation course. The Scientist Interview Preparation course for BARC, ISRO, DRDO, NIC and other central PSUs. Subject Power Electronics. Topic Rectifiers. A continuation of rectifier topics that I am going to discussing. Students, all of you welcome to the session. Myself Surendra Babu. With respect to power electronics, I already given the questions, that is interview questions with respect to power semiconductor devices. Now I am discussing the rectifiers related questions. The previous session also I given some models of questions with respect to rectifiers. In continuation of that, we will see the other models of questions in rectifiers, that is AC to DC converters. Yes friends, all of you welcome to the session. This is also one of the most important model of question asking in interview preparation, mainly for interview point of view, different PSUs. Rectifier feeding industrial electrolysis tank. This is highly non-linear load example. Rectifier feeding industrial electrolysis tank. This electrolysis tank is having so many applications, so many practical applications. What are the applications of electrolysis tank? At the end of that I will discuss. Based on this application, the questions are framing in interview different PSUs. The first question, for rectifier feeding industrial electrolysis tank, can you draw the circuit diagram or industrial setup? Students, here it is not given that it is the uncontrolled rectifier or phase controlled rectifier. If it is not given uncontrolled or phase controlled rectifier, you have to take the phase controlled rectifier only. In phase controlled rectifier, generally you have to take the full wave rectifier. This setup is using the 3-phase full wave rectifier. This is the 3-phase full wave rectifier. A small correction here. How to take? This is the thyristor. These thyristors are like this one. This is the thyristor. Both are in upward direction only. How to correct this? I am taking this correction. Yes. This thyristor, this is the T3 thyristor and T5 thyristor. This is a 3-phase fully controlled rectifier configuration. 3-phase students, fully controlled rectifier configuration. Okay, this is T1, this is T3, this is T5, and this is T4. These are also thyristors. T6, T2, T4, T6, T2. Okay. The input is supplied through 3-phase transformer, or directly we can connect the 3-phase AC source also. Directly connect 3-phase AC source, or we can connect through 3-phase transformers. This 3-phase transformer is optional here. Connect 3-phase AC source directly, or it is connected through 3-phase transformers. If they ask the question, can you draw the circuit diagram for this industrial setup? Then you have to take the industrial setup like this. Take the a full controlled rectifier, that is the fully controlled rectifier. Full controlled converter, that is the fully controlled rectifier. Using the 3-phase fully controlled rectifier. This is the 3-phase fully controlled rectifier. Okay. Then the output of the rectifier is given to the electrolysis tank. This is the electrolysis tank is the DC load. Important question. What about this electrolysis tank? It is a which load? It is a DC load. Here back EMF is nothing but due to chemical reaction there is a EMF. Actually it is not a motor load. It is electrolysis tank. It is having a DC load. Because of chemical action there is a EMF. That EMF is generally to take as a back EMF or simply it is a EMF. Generally in the motor we are taken as it is a back EMF. Here simply you take EMF or back EMF. Okay. This is the industrial setup. But whatever the load we are consider here, that load is highly non-linear load. This load is having low resistance and EMF. This load, whatever the electrolysis tank na, this load is the having the low resistance and EMF. That's the why EMF here, electrochemical reaction. Because of electrochemical reaction there is a EMF. It is a high non-linear current. High non-linear current. How the question is asking here? They will give this application. Can you draw the industrial setup? Then you have to draw like this. Then the output of the rectifier is given through smoothing reactor. The purpose of using, what is the purpose of this smoothing reactor? To reduce the ripple. To reduce ripple in load current. Ripple in load current. For that purpose we are using the smoothing reactor. Clear? Next. Can you draw the output DC current waveform? Yes, this is the output DC current waveform. Here it is asking. Then the output of the three-phase full wave rectifier. Output of the three-phase full wave rectifier. It is a nearly constant current waveform. Or by considering some ripples also you have to draw. This is the DC current waveform. By considering some ripples also you have to draw the waveforms. Like this we can get the DC current waveform for one cycle. Okay, or simply you can draw a constant current waveform also, that is also called. But this is the output DC current waveform. Continuous current due to large smoothing intervals. Why are you getting the constant current? Or simply you can draw like this also. We can draw a constant current waveform like this. This constant current, or you have to take like this. You have to draw a constant current waveform structure. This is because of the high inductance. If there is a high inductance, you reduce the ripples, then you have to take this as the constant current wave. Therefore, ID equal to ID average plus delta ID. Ripples is small if L is large. That I told. What the purpose of using this inductor? To reduce the ripples in the current, load current. To reduce the ripple in the load current. This one more question. Draw the current waveform. Then you have to draw the output current waveform of the full wave rectifier. Three-phase full wave rectifier. Next. Can you draw the input AC line current waveform? Input AC line current waveform. You can get the shape like this. This is the input AC line current waveform. We are getting the input AC line current waveform. Like this. Approximately I am drawing the waveform. Approximate waveform. You have to draw like this. It is a non-sinusoidal line current. This is having very rich in harmonics. Here two questions. Can you draw the output DC current waveform? Draw the waveform like this. Can you draw the input AC line current waveform? Draw the like this. This is the input AC line current waveform. But whatever the current drawn at input side, it is not a sinusoidal current. It is a non-sinusoidal current. Okay. It is a non-sinusoidal current. This current is a non-sinusoidal current. That's why input is very rich in harmonics. Therefore, input is very rich in harmonics. Very rich in harmonics. Very rich in harmonics. Okay. Next. What is the average output DC voltage? This is important. Sometimes they will ask the formula also. Can you write the sorry, what is the average output voltage of 6 pulse converter? Yes, we know that what are the 3-phase fully controlled rectifier? This 3-phase fully controlled rectifier is how many pulse converter? 6 pulse converters. 6 pulse converter. Then for this 6 pulse converter, what the ripple frequency they ask? What the ripple frequency? Ripple frequency equal to 6f. The ripple frequency that is output ripple frequency. Output, not input. It is output ripple frequency. Output ripple frequency equal to 6f. Okay. Then one more important, can you draw the average output voltage? Then for 6 pulse converter, the average output voltage equal to 3 root 2 by pi VLL cos alpha. We can also write like this. Is VDC or V average equal to, this is the 3 VML by pi cos alpha. Important formula. 3 VML by pi cos alpha. 3 VML by pi cos alpha. The average output voltage is equal to 3 VML by pi cos alpha. This is average output voltage. What is VML here? Maximum value of line voltage. This VML equal to maximum value of line voltage root 2 into RMS value of line voltage. VML equal to root 2 times of R. Just we have to replace VML by root 2 times of VLL. We can get this. What is alpha here? Firing angle. What is VLL? Line to line RMS voltage. What is VDC? Average DC voltage. This also average voltage. V naught or VDC, any notation you have to follow, students. Average voltage. For the average output voltage. Then can you relate the electrolysis rate with respect to firing angle? If the question is asked like this, can you relate how this electrolysis will change with respect to firing angle? Concept very simple. If alpha is increases, or the average output voltage decreases. Alpha increases, average output voltage decreases. Then the electrolysis rate is also decreases. If alpha decreases, average output voltage is increases. Then average output voltage is increases. Then electrolysis rate will increase. Like this, we can relate the firing angle and electrolysis rate. Because why the question is asking electrolysis rate? Here the load is which one? Electrolysis tank. That is the DC load. Electrolysis tank is the one of the DC load. That is how we can control. Therefore, by controlling firing angle alpha, by controlling firing angle alpha, electrolysis rate is controlled. This you have to concentrate. By controlling firing angle alpha, we are controlling the electrolysis rate. In the same case, if it is asked what is the RMS output, this is the average output voltage. If they ask what is the RMS output voltage, VML into root 3 by 2 pi. How to write this? What is the RMS output? The question is asked what is the RMS output? This RMS output voltage. This V naught RMS equal to VML into root 3 by 2 pi into, how to write pi by 3 plus root 3 by 2 cos 2 alpha whole to the power of 1 by. Sometimes they will ask the direct formula also. Sometimes can you derive that one? Try to derive that formula also. You already know in the study of the power electronics subject now how to derive these formulas. That also you have to practice. That is one more important stress. Practice derivation of V0 and V0 RMS. Here I given direct formula, students. You please practice that derivation of V0 and V0 RMS. Can I derive that formula? You try to write the limits also. You try to write the time period. Time period is pi by 3. And you try to write the limits. Then integrate the VML sin omega t with respect to d omega t. Then we can get the what the RMS output voltage, what the average output voltage. This is the average output voltage and this is the RMS output voltage formula. This is for which converter? 6 pulse converter. 6 pulse converter is nothing but 3-phase full wave rectifier. Therefore, by controlling the firing angle, we are controlling the electrolysis rate. We are controlling the electrolysis rate. Next. One more question in this application. What is the application I am explaining here? Yes. How we are controlling the electrolysis rate by using the rectifier. This electrolysis load is nothing but a non-linear. Electrolysis tank is controlled by using the rectifier. Rectifier feeding industrial electrolysis tank. Rectifier feeding industrial electrolysis tank. These are the possible questions. I am explaining all the possible questions. These models already framed in interview. These models of questions already framed. Then can you draw the total harmonic distortion versus load current? What the THD stands for? What the THD stands? This THD stands for total harmonic distortion. Total harmonic distortion. Total harmonic distortion. If the question is asked, can you draw the total harmonic distortion versus load current? Yes. If the load current is increases, the harmonic distortion is going to decrease. Important observation. If the load current is increases, the harmonic distortion is going to decrease. THD is high at light load and decreases as load current is increases. At light load, the total harmonic distortion is high. As load increases, or the total harmonic distortion is going to decrease. This you have to concentrate. What is the total harmonic distortion? And one more important here, we can expect. Okay, you are telling that as the load is increases, the total harmonic distortion is decreases. Can you write the formula for fundamental component of source current? Fundamental source current. If the question is asked like this, what is the value of fundamental source current? Fundamental source current. Then fundamental source current IS1 equal to root 6 by pi into I0. That's important. Root 6 by pi into I0. Can you write the formula for displacement factor? Display input, all these are input sides. Input displacement factor. The input displacement factor equal to cos alpha. Can you write the formula for input power factor? The question is asked, or the input power factor form. This is equal to 3 by pi cos alpha. All these are which one? 3-phase full wave rectifier. Full wave rectifier. All these are points for 3-phase full wave rectifier. This question already framed. Can you draw the characteristics THD versus load current? As load current is increases, the THD is going to decreases. Next. Why harmonics are high? You are telling that for in this load, the harmonic content is more. The reason is non-linear load. Electrolysis process draws pulsating DC current, not a sinusoidal current. Not sinusoidal. It drawing the pulsating DC current. It's not a sinusoidal. That's why it's a non-linear load. Rectifier switching. SCRs conducts in discrete intervals. SCRs conducts in discrete intervals. Discontinuous or distorted line current. At light load, current pulses are narrow, higher distortion. There is a distortion of the input current also. No sinusoidal current shaping device at input. high harmonic current. That's why whatever the input current, input current is also non-sinusoidal. Yes, friends. Input current is also non-sinusoidal. Also non-sinusoidal. Then because of this reason, the harmonic content are high. The question is asked for this question, why harmonics are high? Because of non-linear load. The main answer for this question is because of non-linear loads. Then is there any other reasons? Then explain like this. Electrolysis process draws pulsating DC current. Rectifier switching is not in SCRs conducting in discrete intervals. What is the conduction of device? T1, T6, then T2, T3, then like this discrete intervals. Each SCR conduction angle is 120 degrees. Discontinuous or distorted line current, even line current, the input current is also non-sinusoidal. Because of all these reasons, the harmonic contents are high steps. Next, how to reduce harmonics? In this case, in this application, how to reduce harmonics? One method is increase the smoothing inductor. Increase the smoothing inductance. If the inductance is increased, pulses are reduced, harmonics also reduced. Instead of 6 pulse, you have to use the 12 pulse or 24 pulse converter. Instead of 6 pulse converter, you have to use 12 pulse converter or 24 pulses. If the pulse number is increases, the harmonic content is reduces. This one of the configuration to get the 12 pulse. 6 pulse converter group 1, 6 pulse converter group 2. Then this is the 12 pulse converter. You have to use either 12 pulse or 24 pulse converter. Then because of this, it cancels the 5th harmonic, 7th harmonic, 17th order, 19th harmonics. Then lower THD. The THD will be reduced. 12K. See, if you use the 6 pulse converter, if you use 6 pulse converter, the harmonics are 6K plus or minus 1. If you use the 12 pulse converter, the harmonics are 12K plus or minus 1. See, for 6 pulse converters, friends. For 6 pulse converter, what is the order of harmonic? Order of harmonic equal to 6K plus or minus 1, where K equal to 1, 2, 3. This is order of harmonic. What is N here, friends? Order of harmonic. Order of harmonic. Okay. Then if you substitute K equal to 1, 2, 3, then what is N? You can get 5, 7, 2 you substitute, 12, 11, 13 and so on. This is the dominant harmonic is 5, 7. Dominant is 5, 7. Dominant is 5, 7. That is, there is no any triplet harmonics. No triplet harmonics. All the triplet harmonics are absent in 6 pulse converter. If you use the 12 pulse converters, 12 pulse. For 12 pulse converter, what is the order of harmonics? 12K plus or minus. This is at input side, 12K plus or minus. If 12K plus or minus, this is at input side, at input harmonics. At input. Now substitute K equal to 1, 2, 3 and so on. K equal to 1 you substitute. Then 11, 13. 11, 13. Then if you use this one, 11 and 13, 5, 7 is eliminated. If you use the 24 pulse converter, then the 17th and 19th order is also cancelled. Then all the low order harmonics are cancelled. That is more advantage. That's why by using 12 pulse converter or 24 pulse converter also we can reduce the harmonics. Then using the passive filters also we can reduce the harmonics. Use tuned LC filters to trap specific harmonic orders. Active harmonic filters also you have to use. Inject equal and opposite harmonic currents, then you cancel that one using active harmonic filter. What is the concept in active harmonic filter? Injects equal and opposite harmonic currents, then cancel that harmonics. Then by increasing the load current, just now I told, if load current is increased, what the harmonic content will decrease. That is also one more method. By increasing the load current also, we can reduce the harmonics. By increasing the load current also, we can reduce the harmonics. Clear? The question is asked how to reduce harmonics. Like this you have to answer. Okay. Next. Flat harmonic spectrum. Then if you use for 6 pulse converter, this is the fundamental component. Next 5th order, 7th order, 11th order, 13th order, 17th order, 19th order, 20th. Then which are the dominant harmonics? Mainly 5th and 7th is the more dominant harmonics, most dominant harmonic. Next 11th, 13th, 17th, 19th order. Then if you use 12 pulse and 24, either 12 pulse or 24 pulse. If you use 12 pulse, there is no 11, there is no 5th order and 7th order. If you use the 24 pulse, there is no 11th and 13th and 17th order harmonics also. Because 24k plus or minus 1, k equal to 1. K equal to 1 means then you substitute 25 or 23. Then 19th order harmonic is also. Understand? That's why if he is asked for harmonic spectrum, then which is the dominant harmonics? 5th order. This is the fundamental component. Fundamental is not harmonics. This is the fundamental. How the question is asking? Can you draw the harmonic spectrum? Like this you have to draw the harmonic spectrum. This is for which one? For 6 pulse converter. This is for 6 pulse converter. This harmonic spectrum is drawn for 6 pulse converter. This is for 6 pulse converters. That you have to consider. Next. Then what are the applications of rectifier feeding electrolysis tank? Where you have to use this electrolysis tank? Yes. Aluminum smelting, copper refining, chloralkali process, that is NaCl electrolysis process, water electrolysis process, hydrogen production, that is hydrogen production, electroplating industry. In all these applications, we have to use this electrolysis tank, rectifier feeding electrolysis tank. For rectifier feeding electrolysis tank, where you have to use, if the application point of view, if the question is asked like this, you have to. What are the requirements for this application, electrolysis tank application? High DC current is required, controlled DC voltage is required, low ripple and stable operation is required, low harmonic distortion is required. Then benefits of harmonic reduction. Then how to reduce the harmonics that I told now. What is the benefits of reducing the harmonics? If the question is asked. Improve the power factor, reduce heating and losses, increase equipment life, better supply quality. This is advantage of reducing the harmonics. Then final conclusion point. Electrolysis load is highly non-linear load. Rectifier is non-sinusoidal input current. Total harmonic distortion is high due to switching and discontinuous conduction. Harmonic distortion will reduce if the load is increases. Use 12 pulse filters and inductors to reduce the harmonics. Okay, this final observations. Okay, this about the what application of rectifier feeding electrolysis tank. How the questions are asking, how to answer those questions. Maximum in this application, the questions are asking harmonics point of view. Harmonics point of view, you can expect the questions. Okay, what type of harmonics are present if you use this configuration? Then how to reduce this harmonics? If you reduce the harmonics, what is the advantage? Okay, yeah, that type of question is. In formulas point of view, yes, you are using a 3-phase full wave rectifier. Can you draw the current waveform for this? Can you draw the voltage waveform for this? Can you explain the conduction of these devices? That you have to practice. Can you explain the conduction of the devices? Yes, students. Then can you write the average output voltage formula? Can you write RMS output voltage formula? Can you derive the average and RMS voltage formula? What is the displacement factor formula? What is the input power factor formula? All this I given. What is the RMS value of the fundamental source current? Okay, we can also expect for this full wave rectifier if the question is asked, you have to concentrate what is the RMS value of source current. RMS value of source current. This Is equal to I naught into square root 2 by 3. What the average value of each thyristor current? Average. Each thyristor is conducting how many degrees? 120 degrees. Then average value of each SCR current. Average value of each SCR current is I naught by 3. What is the RMS value of each SCR current? RMS value of each SCR current. If they ask what is the RMS value of each SCR current, that you write I naught by root. I naught by root. Like this you have to write the formulas. We can expect the formulas. We can expect the conduction of devices. Okay. We can expect the circuit description. We can expect the questions on the harmonics. Like this you have to practice. Next. One more application. In the rectifiers itself, one more application. Three-phase uncontrolled rectifier in steel plant. Important. Three-phase uncontrolled rectifier in steel plant. How the questions will ask. Okay. The circuit diagram of three-phase uncontrolled rectifier. Three-phase uncontrolled rectifier is nothing but it is a three-phase diode rectifier. Three-phase uncontrolled rectifier is nothing but it is a three-phase diode rectifier. But previously they don't give a rectifier name. Then I taken which one? Fully controlled rectifier I taken, that I explained. This is the three-phase uncontrolled rectifier. Three diodes. D1, D3, D5 and D4, D6. This is all these are the common cathode configuration. All these are the common anode configuration. This is the positive group and this is the negative. Top diodes D1, D3, D5 is positive group. Bottom diodes D4, D6 is negative. Each diode conducts 120 degrees. Can you draw the three-phase waveform? Then draw the waveform like this. Can you draw the circuit diagram? This three-phase uncontrolled rectifier using the steel plant. Using the steel plant, how to draw like this. This is using uncontrolled rectifier. This is a three-phase AC source. This is the three-phase AC source. This is applied to uncontrolled rectifier. Yes, friends. Then one more question we can expect. Can you write the output voltage? Here circuit diagram waveform. Can you write the output DC voltage waveform pulses? Then output DC wave, it is a 6 pulse per cycle. How many number of pulses per cycle? 6 pulses. 1, 2, 3, 4, 5, 6. 6 pulses. How much angle each diode is conducting? Each diode is conducting 120 degrees. Can you write the conduction sequence? Yes, this is the conduction sequence. D1, D6, D1, D2. Then D3, D2, D3, D4, D5, D4, D4, D5, D5, D6. This is the sequence of conduction. You can also expect the sequence of conduction of it. Then what is the average output voltage? This one. The average output voltage V0 equal to. This is 3 VML by pi. But there is no cos alpha here because the diode rectifier. No firing angles. But what is the VML here? Maximum value of line voltage. VML equal to maximum value of line voltage. Root 2 into VLL. This we have to write T root 2 VLL. Yeah, this is the average output. This is the output of the three-phase full wave uncontrolled rectifier. That is the three-phase full wave rectifier. In this case also, what is the ripple frequency if it is asked? How to write the ripple frequencies. The ripple frequency equal to 6 times of. Because how many number of pulses per cycle equal to 6? Number of pulses per cycle equal to 6. Then how the question is asking here? Can you draw the line current waveform? Yes, same line current waveform. Like this I am getting that. It is just like a quasi-square wave. Line current is non-sinusoidal. Even in the three-phase fully controlled rectifier and uncontrolled rectifier also, this is one phase I am drawing. For remaining phases also you can get like that. That's why what is the input current for each phase? It is a sinusoidal or non-sinusoidal? It's a non-sinusoidal. It's a quasi-square wave. Just like a quasi-square wave. What is the shape of this? we are getting the quasi square wave. Okay, it is a quasi square. Then what the line current? Line current is which waveform here? The line current is non-sinusoidal. The line current is the non-sinusoidal. Each line current, in each line current conducts for 120 degrees. That is, each diode conducts for 120 degrees. Discontinuous in nature, that is rich in harmonics. This is the question is asked. In interview, this question is asked. Can you draw the line current waveform? Yes, you draw the line current. Students, once you prepare already power electronics 3-phase diode rectifier, full wave diode rectifier, then answering these questions are very easy. Just application point of view, they are asking the harmonics analysis. Then what is the harmonic order in line current? It is also 6 pulse converter. Then order of harmonics, we have to use either H or N. The order of harmonic N equal to or H equal to 6k plus or minus 1. Then which order it present? 5th order, 7th order, 11th order, 13th order, 7th order. It is a 6k. 6 pulse converter, 6k plus. It is also 6 pulse converter. This is how many pulse converter? It is a 6 pulse converter. It is a 6 pulse converter. It is a 6 pulse converter. What is the order of harmonic? This one. That is in the output. What are the harmonics? This is the input harmonic in line current. This is the input harmonic, not output harmonics. Input harmonics. Input harmonics. Okay. Then there is no triplet harmonics. That is, triplet harmonics are absent. There is no 3rd order, 9th order, 15th order like this. Triplet harmonics are absent. Which harmonics are absent? Triplet harmonics are absent. Just like a electrolysis application, even steel plant application, we are using uncontrolled rectifier also like this. Triplet harmonics are absent. Then what is the RMS value of the H order, Hth order or nth order? Either H, some authors they follow in H notation, some authors they follow in N notation. Here I taken H order. Then this is the RMS value of the H order harmonic. Where Im equal to the peak value of line current, IH equal to RMS value of H order harmonic. What is the RMS value of it? Then if they ask, write the formula, write down this formula. What is the RMS value of H order harmonic? 4Im by pi H pi. Or you have to use 4Im by N pi. Nth order means N. H order means H. That's the only difference. This question is also important. Can you explain what is the order of harmonics? Write the RMS value of H order harmonics. Next, again, same model of question it is asking. Can you write the harmonic spectrum? Harmonic spectrum is, this is fundamental. Then which is the first two dominant? 5th order is dominant. Next 7th order is dominant. Next 11th order is dominant. Next 13th order, 17th order, 19th order, 23rd order, 25th order. If order of harmonic is going to decreasing, the dominant percentage of harmonic is going to decrease. Highest value is fundamental. Next 5th order, which is the most dominant harmonic here. 5th and 7th order is most dominant harmonic. Low order is having higher magnitude, sir. Very important. This is important. If order of harmonic is increases, magnitude is decreases. If order of harmonic increases, the magnitude is decreased. If order of harmonic is increases, the magnitude is going to decrease. That's why 25th order is having low magnitude, but 5th order harmonic is having high magnitude. 5th order harmonic is having high magnitude. Next, why 5th and 7th order harmonics are dominant here? Important. Why 5th order and 7th order harmonics are dominant? Students, we know that due to 120 degree diode conduction pattern, we are getting 6-step waveform. The Fourier series for 6-step waveform consists of 6k plus or minus 1 harmonics. Low order harmonics have higher magnitude. In harmonics point of view, if you apply the Fourier analysis, then which order is having the higher magnitude? Low order having the higher magnitude, because the amplitude of harmonics is inversely proportional to the order of harmonic. If order of harmonic is less, the amplitude is more. That's why the triple N, third, ninth, fifth is cancelled here. That's why most dominant is the fifth order. Most dominant is fifth and seventh. It is not a third order. Why? Third order, ninth order is cancelled. That's why most dominant is fifth and seventh. That's why hence fifth and seventh order are the most dominant order. The question already framed like this. In interview, all these are the interview questions. Can you explain why fifth and seventh order harmonics are dominant? This is the reason. Already third order is cancelled because of the stepped waveform, 6-step waveform. Third order is cancelled. Then amplitude of harmonic is inversely proportional to n. If n is going to decrease, amplitude is increasing. That's why low order is having the more dominance. Next. What is the impact on grid? This question is also there. What is the impact on grid? Yes. Because of this harmonic, what is the impact? Then power quality issues. The question is based on the power quality issues. Low power factor, distorted current reduces the power factor. Because of the input current is the distorted current. Because of distorted current, the power factor will be reduced. Heating of the equipment, extra losses in transformer and cables. Because of the distorted current, that is harmonics are more. Because of more harmonics, more losses, the transformer and cables, the losses will be increased. Voltage distortion affects nearby sensitive loads. It will affect the more effects on the sensitive loads. Resonance problems also will come. Many may interact with the capacitors, power factor panels. That is the resonance problem will occur. Malfunction of the equipment, relays, sensors, drives may trip or overheat. That is the impact on the grid because of the non-sinusoidal input current if harmonics are increases. See, once we are using the uncontrolled rectifier, output is applied to the steel plant. The input current drawn is the non-sinusoidal. When the input current drawn is non-sinusoidal, this impact is on the grid. Because of non-sinusoidal current, this affects the grid performance. What it will affect? It affects the power factor. And then heating of equipment it will cause us. It affects the nearby sensitive loads also it will affect. Resonance problem it will cause us. Malfunctioning of equipment also it causes. Then overall results is poor power quality, higher losses, reduced reliability. This is the overall result. If you use this arrangement, there is overall results is poor power quality, higher losses and reduced reliability. Then alternative arrangement. You have to reduce the harmonics. I told already. We have to use the 12 pulse converter. Using 12 pulse converter, you have to reduce the harmonics. Once we can use 12 pulse converter, 5th and 7th order harmonic is eliminated. The dominant harmonics 11th. Why? In 12 pulse converter, what is the order of harmonics? 12k plus or minus. Where k equal to 1, 2, 3 and so on. 1, 2, 3 and so on. N equal to 12k plus or minus 1. Where k equal to 1, 2, 3. This is the order of the harmonics. Therefore, by using 12 pulse or 24 pulse rectifier, the order of harmonics, low order harmonics are eliminated. Passive filters. Using passive filters also, using active power filters also you have to use. You have to use the line reactors at AC side to reduce harmonic current. Proper transformer design is also required. Then by using this, we can reduce the harmonics. We can reduce harmonics. We can reduce harmonics as well. Then power quality is improved. Power quality improved. Yes, students, in this session I explained two important applications of the rectifiers. In these two important applications, nearly 13 to 15 questions, how the questions are asked, that I explained. All these models of questions already framed in the interview in different PSUs. That is 3-phase uncontrolled rectifier in steel plant. That is one application. 3-phase uncontrolled rectifier in steel plant. Application of rectifier feeding electrolysis tank. Electrolysis tank application and steel plant. By using the one is I explained with respect to fully controlled rectifier. The another one is I explained about the uncontrolled rectifier. Yes, students, one model of questions in interview application oriented diagram. You ready to draw this one? Next, the another model is directly the questions from rectifier. You are using the 3-phase uncontrolled rectifier. Yes, draw the circuit, explain the operation of the circuit, what the conduction of the devices, what the average output voltage, what the RMS voltage, what the circuit turn off time. This you already prepared in the subject also. That type of questions answering is very easy. But in application oriented harmonics concept, if load current is increases, what happened to the harmonics? Then how we can reduce the harmonics? If you use the 6-pulse converter, which is the dominant harmonic. If you use the 12-pulse converter, which is the dominant harmonic. If you use the 24-pulse converter, which is the dominant harmonic. That type of questions, how to answer that I explain. Next, what is the effect on the grid performance? When I use this type of arrangement, what is the effect on the grid? Then because of the harmonics, whenever input is having harmonics, which directly affects the grid performance also. Because of the harmonics, then losses will be increases. Once the losses are increases, this will affect all the equipment also. This will affect the load also. Then this will affect some protecting devices also. It will be affected because of the harmonics. Okay, these are the cause. Because of harmonics, we are getting all these problems. Then how to reduce that harmonics? Explain like this. What methods we have to use to reduce the harmonics? Yes, friends. In this session, I explain about the 2 important applications of the rectifiers in detail that I given. How the questions are asked, nearly 13 to 15 questions that I explained, that you have to concentrate, students. Okay. The next coming session also, next 1 or 2 sessions also rectifiers will come, rectifier related questions will come. After that, we will see the choppers, inverters, and AC voltage controllers, cyclo converters and drives. It's about the session. Thank you.